Whenever the word cosmos is mentioned, your mind likely paints a picture of a boundless, dark expanse peppered with shimmering stars, a timeless image that has been with us for ages. Yet, the truth is vastly more intricate than this initial impression suggests. The universe is not merely a collection of stars, planets, and the emptiness separating them. It is a colossal, elaborately woven fabric of unseen forces, energies, and events that we have just started to grasp. The reality you perceive directly is only a minuscule portion of what truly exists, as our eyes are confined to a very thin band of the electromagnetic spectrum known as visible light. The rest of the spectrum, which includes infrared, ultraviolet, radio waves, X-rays, and gamma rays, is completely concealed from our sight. It is precisely within these invisible frequencies, however, that the bulk of the universe's secrets are encoded. Consider that many stars that barely register in visible light actually blaze with intensity in the infrared. Other celestial bodies, practically imperceptible to the naked eye, are potent sources of X-ray radiation, often signaling the aftermath of supernova explosions or the turbulent centers of galaxies. In these galactic cores, matter spirals into a black hole and is heated to billions of degrees, a spectacle we cannot witness directly, but can detect with instruments that interpret these cosmic signals for us. The apparent blackness of space is deceptive, as it is not entirely empty. Drifting between the stars and galaxies are vast clouds of interstellar gas and dust, so sparse that a cubic meter might contain just a handful of atoms. Despite this extreme low density, this near-perfect vacuum is still capable of absorbing, reflecting, and scattering light, and over immense timescales, these clouds collapse under their own gravity to become the birthplaces of new stars. The universe is in a constant state of flux, with stars being born and dying, galaxies merging in cosmic collisions, planets being ejected from their orbits, and black holes consuming matter while spewing out tremendous jets of energy. While you might assume these processes unfold at an incredibly slow pace, time operates on a completely different scale in the cosmos. An event that takes millions of years to complete is, from a universal perspective, merely a fleeting moment. An equally mind-bending aspect of the cosmos is that you are always observing it as it was in the past. The light from our sun takes 8 minutes to get to you, while light from the closest star travels for 4 years, and light from remote galaxies journeys for billions of years. Consequently, every time you gaze at the night sky, you are essentially looking into a cosmic time machine, witnessing history unfold across the universe. Throughout this discussion, I will guide you through some of the most spectacular phenomena and enduring puzzles of the universe. We will delve into topics like dark matter and dark energy, examine the cycles of stellar birth and death, explore how planets are formed, and consider the profound connection between the cosmos and you. You will come to understand that the immense blackness of space is, in reality, saturated with light that our senses just aren't equipped to detect. Your typical image of the cosmos is probably one of a frigid vacuum, a place without air or warmth where temperatures hover near absolute zero. While there is truth to that perception, the universe is not uniformly cold. It is a domain where areas chilled to the brink of absolute zero exist alongside regions superheated to tens of millions of degrees. This may sound like an unbelievable paradox, but it is simply a consequence of fundamental physical laws at play. The baseline temperature of deep intergalactic space measures approximately 2.7 Kelvin, which is -273.15 degrees Celsius. This pervasive chill is due to the cosmic microwave background, also known as relic radiation, which is a faint thermal afterglow from the Big Bang that fills all of space. This radiation comes at us evenly from every direction, marking the era roughly 380,000 years after the universe's origin, when it first became transparent to light. However, if you shift your focus to an area of active star formation, or the vicinity of a feeding black hole, the temperatures skyrocket to unimaginable levels. For instance, our own Sun has a surface temperature of about 5,500 degrees Celsius, but its outer atmosphere, the corona, can reach between 1 and 2 million degrees. There's no consensus on why this happens, but researchers believe it's connected to intense magnetic fields that whip charged particles up to incredible velocities. Space also hosts even more intensely hot environments, such as the areas surrounding supernova explosions, where temperatures can spike to hundreds of millions of degrees. These cataclysmic events are not just destructive, they are also fundamentally creative, as they forge and scatter the heavy elements required for the formation of planets, atmospheres, and ultimately, life itself. Conversely, some locations in the universe are even colder than the cosmic average. A prime example is the Boomerang Nebula, situated roughly 5,000 light-years away, where the temperature plunges to a mere 1 Kelvin, just a single degree above absolute zero. This profound chill is caused by gas being ejected from a dying star and expanding so quickly that it loses heat far more rapidly than it can absorb it from the background radiation of space. You must realize that temperature in the cosmos is not something you would experience in the same way as on Earth. It isn't a measure of ambient warmth, but rather the kinetic energy of individual particles. You could find yourself in a region where particles are heated to millions of degrees and still freeze to death, because the matter is so diffuse that almost no heat would actually be transferred to your body. This stark interplay between extreme heat and cold is what drives the distinct dynamics of the universe. The coldest regions serve as stellar nurseries, where gravity can pull gas clouds together until they are dense enough to ignite nuclear fusion. In contrast, the hottest zones frequently signify the violent conclusion of a star's existence, as it erupts in an explosion that obliterates its surroundings. So, it becomes clear that the cosmos is far from being a simple, dark, and frigid emptiness. It is more like an immense tapestry upon which icy nebulae and incandescent gas clouds, serene intergalactic stretches, and violent stellar cataclysms are all interwoven. Perhaps this fundamental duality is what has allowed our universe to become so rich with diverse forms, and ultimately, life. When you look up at the canopy of the night sky, it may appear to be a fixed dome, but you are in truth staring into the profound depths of space and time itself. Every glimmer of light you observe in the night sky is a message from the past, turning you into a reader of a cosmic history written in light. The velocity of light is finite, at approximately 300,000 kilometers per second, a staggering speed on Earth, yet surprisingly modest across the vastness of space. As a result, the sunlight you feel arrived after an 8-minute and 20-second journey, showing you the sun as it was moments ago, while the light from our nearest stellar neighbor, Proxima Centauri, has traveled for over 4 years to reach you. The Andromeda Galaxy is an even more extreme example, appearing to us as it existed 2.5 million years in the past. Remarkable instruments like the James Webb Space Telescope and its legendary predecessor, Hubble, empower us to look even further back in time. Astronomers are now analyzing light that has journeyed from more than 13 billion years, providing a direct view of objects from the universe's infancy, just a few 100 million years after the Big Bang. This brings us to the cosmological horizon, a fundamental boundary beyond which we cannot see, defined by the universe's age of about 13.8 billion years. Essentially, light from anything more distant simply hasn't had the time to reach us. Yet because space itself is expanding, the ancient objects we now see at this edge are currently located around 46 billion light-years away from our position. When you gaze into these profound depths, you do not find the orderly spiral galaxies familiar to us. Instead, what you witness are small, faint, and chaotic knots of light, which represent the very first galaxies in the process of assembling their structures. You are seeing the birth of the first stars, as gravity slowly condenses scattered clouds of hydrogen into massive celestial bodies that ignite, beginning the process of transforming the universe with their radiating light and heat. By examining these primeval objects, you're not merely observing distant points of light. You are studying the intricate process of cosmic evolution itself. These early galaxies were deficient in heavy elements, as those materials had yet to be forged in the nuclear furnaces of stars. As generations of stars perished in supernova explosions, they enriched the cosmos with the very elements that, billions of years later, would form planets and eventually give rise to life. There's a profound philosophical weight to this, as looking at the universe's edge makes you a witness to events that occurred long before our own sun, let alone the Earth, ever existed. Imagine if you could sense the universe, not with your eyes, but through the force of gravity. You would immediately realize that everything we perceive as the cosmos, stars, planets, and galaxies, is but a tiny fraction of a much grander structure. The astonishing truth is that all visible matter constitutes only about 5% of the universe's total mass and energy. The remaining 95% is entirely hidden from our view, composed of approximately 27% dark matter and 68% dark energy, which we'll explore later. So, what exactly is this crucial yet elusive dark matter? It is a substance that does not emit, absorb, or reflect any light, making it completely transparent to all forms of electromagnetic radiation, and thus impossible to see directly. We are only aware of its existence through its powerful gravitational effects. This incredible story began in the 1930s with the work of Swiss-American astronomer Fritz Zwicky, who, while studying a galaxy cluster in the Coma Berenices constellation, noticed that the galaxies were moving far too rapidly. Their speed should have flung them apart unless an enormous amount of unseen mass was providing the necessary gravitational cohesion, a substance he termed dunkle Materie, or dark matter. Further confirmation came in the 1950s from American astronomer Vera Rubin, who studied the rotation of spiral galaxies. She discovered that stars on the galactic outskirts orbit just as quickly as those near the center, a phenomenon that violates the laws of physics if only visible matter is considered. Her work demonstrated that each galaxy must be enveloped in a massive halo of dark matter. Today we find indirect evidence for dark matter everywhere, from the bending of light from distant galaxies by unseen mass in a process called gravitational lensing, to the subtle temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang. Several hypotheses attempt to explain the nature of dark matter. The leading candidates include weakly interacting massive particles, or WIMPs, which would rarely engage with normal matter. Hypothetical lightweight particles called axions, thought to pervade all of space, or sterile neutrinos, a variant of the neutrino that interacts solely through gravity. Scientists have constructed incredibly sensitive detectors in a global effort to capture a single dark matter particle, but these searches have so far been unsuccessful. This lack of direct detection, however, does not diminish its necessity, as our understanding of why galaxies hold together and why the universe has its large-scale structure depends entirely on its existence. In essence, dark matter provides the invisible foundation upon which the entire architecture of the cosmos is constructed. Although unseen, it dictates the formation and location of galaxies, stars, and planets, meaning that without its influence, we ourselves might never have come to be. We find ourselves living in a reality where the vast majority of existence is concealed from us, yet everything we can see is utterly dependent upon it, marking this as one of the greatest scientific mysteries of our time. If dark matter serves as the cosmic glue binding galaxies and their clusters together, then dark energy functions as its complete opposite, a repulsive force driving them apart. This force is the very reason the universe's expansion is not only ongoing, but is also accelerating, a discovery that stands as one of the most startling and poorly understood breakthroughs in modern cosmology. Until the close of the 20th century, the scientific consensus was that gravity should be causing the universe's expansion, which began with the Big Bang, to gradually slow down over time. The combined gravitational pull from every star, planet, gas cloud, and even dark matter was expected to steadily slow down the universe's expansion. However, during the late 1990s, two separate teams of astronomers examining remote Type 1a supernovae, which are stellar explosions of a known luminosity, discovered these events were dimmer than anticipated. This observation implied the supernovae were at a greater distance than models had predicted, leading to a startling revelation. The expansion of the cosmos is not decelerating, but is in fact speeding up. Scientists proposed the idea of dark energy to account for this accelerated expansion, although its true nature remains a mystery. It might be an intrinsic quality of space, what's called the cosmological constant, an idea originally put forward by Albert Einstein. Or it could be the effect of an unknown dynamic field, like the theoretical concept of quintessence. As it stands, dark energy is thought to constitute around 68% of the universe's total mass energy, which implies that a substance we barely understand makes up the vast majority of our cosmos. You can see the influence of dark energy in the way galaxies on the fringes of the observable universe are rushing away from us at incredible velocities. A clear pattern emerges. The more distant a galaxy is, the more rapidly it appears to move away. This isn't because galaxies are hurtling through the void, but because the very fabric of space between us and them is continuously expanding. An intriguing hypothesis considers what the distant future holds if this accelerated expansion persists without end. In billions of years, the majority of galaxies would become completely invisible to us. They would cross our cosmological horizon, a point beyond which their light could never again reach our planet, leaving a future observer in a universe that seems barren and dark, populated only by the handful of galaxies in our local, gravitationally tethered group. Some other potential futures are far more spectacular. The Big Rip hypothesis, for instance, speculates that dark energy's influence could grow stronger with time. If so, tens of billions of years into the future, it might start ripping apart not just galaxies, but eventually solar systems, planets, and even the atoms themselves. Alternatively, gentler possibilities exist where dark energy's properties could shift, causing the expansion to slow or cease, perhaps leading to an entirely different outcome like a big crunch, in which the universe collapses back in on itself. The central challenge is our current inability to observe dark energy directly. We are limited to measuring its consequences and constructing theoretical models based on them. As is so common in scientific inquiry, every new discovery seems to generate even more questions. While dark energy likely holds the answer to the ultimate destiny of the universe, that answer is presently concealed, and we are just beginning the search for the right keyhole. Picture yourself standing inside an immense auditorium just after a deafening sound has erupted. Long after the source goes quiet, you would still perceive subtle echoes and faint vibrations hanging in the space around you. This is a fitting analogy for our universe. Billions of years after the Big Bang, we can still detect its faint reverberation, which we observe not with our hearing, but with sensitive instruments. This afterglow is known as the cosmic microwave background radiation. The existence of the cosmic microwave background, or CMB, a form of thermal energy that permeates all of space, was first predicted on theoretical grounds back in the late 1940s. Physicists reasoned that if the cosmos originated from a singular point of extreme heat and density, its primordial light must still be present, albeit significantly redshifted by cosmic expansion. They concluded this energy would saturate the universe as a uniform, low-temperature glow, which was eventually stumbled upon by American engineers Arno Penzias and Robert Wilson in 1965. During their work with a radio telescope, Penzias and Wilson were attempting to troubleshoot a persistent, puzzling hiss that wouldn't go away, even after they had meticulously cleaned their antenna and verified all their systems. It quickly became apparent that this signal was emanating uniformly from every direction in the sky, marking the first time humanity had ever directly detected the Big Bang's ancient echo. The temperature of this radiation is about 2.725 Kelvin, which is negative 270.425 degrees Celsius, just a fraction above absolute zero. This warmth is the leftover energy from an era when the universe was merely 387,000 years old. Prior to that time, the cosmos was a foggy, impenetrable space. It was filled with a superheated plasma of matter and radiation, where photons were constantly scattered by free electrons, preventing them from traveling any significant distance. Only when the universe cooled enough for electrons and protons to bind into neutral hydrogen atoms could light finally travel unimpeded. And this is the very light we observe as the CMB today. Advanced space-based observatories, including the Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, known as WMAP, and the Planck satellite, have mapped the CMB's structure with incredible precision. Their findings revealed that this background radiation isn't completely smooth. It features minuscule temperature variations, amounting to differences of just millionths of a degree. These slight irregularities, however, were the crucial starting points for the eventual formation of every galaxy, star, and planet. The analysis of this microwave background has enabled scientists to ascertain the universe's age, its overall shape, and the makeup of its contents. Furthermore, the information gathered has served as one of the strongest pillars of support for the Big Bang model. There are also fascinating ideas that venture beyond standard cosmology, such as the notion that the CMB's patterns might contain evidence of ancient impacts between our universe and others, assuming parallel universes are real. Other researchers are scouring the data for imprints of primordial gravitational waves, which may have been generated in the very first moments of the universe's existence. Regardless of these pursuits, the cosmic microwave background radiation essentially provides us with a baby picture of our universe. It shows us how the cosmos appeared long before any stars, planets, or galaxies had formed. When you contemplate that the light from every patch of the night sky has been journeying for almost 14 billion years to reach you, you grasp that we are all part of a truly ancient narrative, whose story is still unfolding. Far out in the cosmos, within the dark and frigid expanses of interstellar space, you can find immense clouds of gas and dust. While they might appear static and devoid of life at first glance, these regions are the setting for one of the universe's most crucial and spectacular events: the birth of new stars. These cosmic nurseries, known as molecular clouds, are where temperatures plunge to only a few dozen degrees above absolute zero. The density of matter here becomes just high enough for gravity to take command. If a slight disturbance occurs, such as a shock wave from a nearby supernova, gravity will start to pull a section of gas and dust together, initiating a collapse. As this clump of matter compresses, its internal temperature steadily climbs over a process that can span millions of years. Eventually, the core of this forming star reaches a critical temperature of about 10 million degrees, which is hot enough to ignite thermonuclear reactions. At this point, hydrogen nuclei begin to fuse into helium, unleashing a tremendous amount of energy, and a new star officially ignites. Astronomers refer to this initial phase of a star's existence as a protostar, which is encircled by a rotating disk of dense gas and dust. It is within this very disk that another incredible story unfolds: the creation of planets. Tiny dust particles collide and merge, building up into progressively larger objects, from small pebbles to planetesimals that can be tens of kilometers across. Over time, these planetary embryos gather more and more material, growing into fully formed planets. Their ultimate composition is determined by their location within the protoplanetary disk. Close to the parent star, where it's much hotter, you'll find the formation of rocky planets like Earth or Mars. Farther out, in the colder regions, planets can accumulate vast amounts of ice and gas, transforming into gas giants such as Jupiter and Saturn. This entire process is not just a magnificent cosmic display. It's also fundamental to understanding our own origins. The Sun and all the planets in our solar system were formed in precisely this manner roughly 4 billion years ago, beginning as a cold cloud, followed by the brilliant flash of a star's birth, and culminating in the assembly of planets, moons, and asteroids. You might find it interesting that most stars don't emerge in isolation, but rather in large families, known as star clusters. While many of these stars eventually drift apart, some remain bound together for billions of years. This suggests that somewhere out in the galaxy, our Sun has sibling stars that were born from the very same cosmic cloud. To study these formation processes, scientists rely on radio telescopes and infrared observatories, which can peer through the thick dust clouds that obscure visible light from young stars. The James Webb Space Telescope has already delivered breathtaking images of these stellar nurseries, revealing enormous pillars and swirling nebulae where new stars are actively being born. When you reflect on this, you might feel a profound sense of connection, because we are composed of the very same atoms that were forged inside stars. We are, in a very literal sense, made of cosmic material. So, when you gaze up at the night sky, you are in a way looking back at your own distant origins. Stars, much like living things, follow a distinct life cycle, from their birth in cold clouds of gas to their end, which can be either a gentle fade or a cataclysmic explosion. The length of a star's life is primarily dictated by its mass. The more massive a star is, the more rapidly it consumes its fuel, and the shorter its existence will be. Our Sun, being a star of average size, is projected to live for about 10 billion years. It's currently around 4 to 5 billion years old, in a stable period called the main sequence, where it converts hydrogen into helium in its core, releasing energy that perfectly counters the inward pull of gravity. In contrast, stars tens of times more massive than the Sun burn through their fuel in just a few million years, while small red dwarfs can shine faintly for hundreds of billions of years. Once the hydrogen fuel in a star's core runs out, it enters a new stage of its life. The star swells dramatically to become a red giant, with its outer layers cooling down as its core contracts and heats up. This increased core temperature enables helium to start fusing into heavier elements, such as carbon and oxygen. And in the most massive stars, this process continues all the way up to iron. This leads to what I call the iron rule of astrophysics. The creation of elements heavier than iron no longer releases energy, but instead requires an input of it. When the core of a massive star becomes saturated with iron, it can no longer generate energy through fusion. Without this outward pressure, the star collapses catastrophically under its own immense gravity. This collapse culminates in one of the most powerful events in the universe, a supernova explosion. In just a matter of seconds, a supernova can emit more energy than our Sun will over its entire multi-billion-year lifespan. It is within the unfathomable heat and pressure of these explosions that the heaviest elements, like gold, platinum, and uranium, are forged and then propelled out into space, becoming the raw materials for new worlds. The fate of a star after a supernova is determined by the mass of its remaining core. If the core is less than about 3 times the mass of our Sun, it becomes a neutron star, a bizarrely dense object where matter is crushed so intensely that atoms themselves are broken down. If the core's mass is greater, gravity's victory is absolute, and the star collapses into a black hole, an object so dense that nothing, not even light, can escape its pull. Stars similar in size to our Sun meet a much more peaceful end. After they have cast off their outer layers, they create a beautiful glowing structure known as a planetary nebula. The core that remains becomes a white dwarf, a very hot but slowly cooling remnant that will gradually dim over billions of years until it becomes a cold, dark cinder. Every star you see is more than just a point of light in the sky. Each one is a cosmic factory, a forge where the elements that make up you and the world around you were created. So, whenever you look up at the stars, you are not only witnessing their present light, but also seeing a glimpse of the future worlds that will one day be built from their ashes. If you can picture stars as individual homes, then galaxies are like sprawling cities filled with billions or even trillions of these stellar homes. These immense cosmic islands, composed of stars, gas, dust, and mysterious dark matter, drift through the boundless ocean of the universe. Every galaxy you see is entirely distinct. Take our own, the Milky Way, which is a spiral galaxy spanning about 100,000 light-years and holding over 200 billion stars. Yet, on a cosmic scale, it's hardly the most massive. Some galaxies are dozens of times larger. For instance, the immense elliptical galaxy IC 1101 stretches more than 6 million light-years across and is thought to house as many as 100 trillion stars. Galaxies are broadly categorized into several primary forms. There are spiral galaxies, such as our Milky Way or Andromeda, which feature graceful arms where star birth is a vigorous and ongoing process. You also have elliptical galaxies, which are typically older and more serene, filled primarily with red stars and very little interstellar gas. Finally, irregular galaxies possess chaotic structures, often the aftermath of dramatic collisions and mergers between other galactic systems. Galaxies rarely exist in total solitude. Instead, they are bound by gravity into groups, clusters, and even vaster superclusters. The Milky Way, for instance, belongs to the local group, an assembly of about 50 galaxies that includes Andromeda and numerous smaller dwarf galaxies. These galactic communities are themselves interconnected, forming a tremendous cosmic web composed of filaments of dark matter, with clusters situated at the intersections, and vast, nearly empty spaces known as voids in between. Remarkably, galaxies lead dynamic lives, constantly interacting, pulling on one another, and sometimes even colliding. A collision doesn't involve stars crashing head-on, as the distances between them are simply too great. Instead, the force of gravity dramatically reconfigures the galaxy's entire architecture, triggering fresh waves of star formation and completely transforming their appearance. In approximately 4 billion years, you can expect the Milky Way and Andromeda to merge, creating a new, giant elliptical galaxy that astronomers have preemptively named Milkomeda. At the heart of nearly every major galaxy, including our own, resides a supermassive black hole. Ours is called Sagittarius A star, and it possesses a mass equivalent to 4 million suns. These cosmic behemoths are instrumental in galactic evolution, as they regulate the rate of star formation and shape the distribution of matter throughout the galaxy. When you reflect on this, it's easy to envision our home as just one of trillions of cosmic metropolises, where every star is a sun that could have its own planets, and each galaxy is but a small neighborhood in the immense expanse of the universe. If you could travel billions of light years from home and observe the universe on its grandest scale, you wouldn't find a random scattering of light. Instead, you would witness a breathtakingly orderly structure, a vast cosmic web woven from the finest filaments that connect enormous hubs. These filaments are made of galaxies, gas, and dark matter, while the voids that separate them are immense regions of near-total emptiness. The sheer magnitude of this structure is difficult to grasp, with each thread capable of extending for hundreds of millions of light-years, and the voids themselves dwarfing thousands of galaxies combined. This entire cosmic structure is a direct consequence of how matter was arranged shortly after the Big Bang, and how gravity subsequently drew it into denser concentrations. Advanced computer models, like the Millennium Simulation, and projects run on NASA supercomputers, reveal that the cosmic web bears a striking resemblance to the cosmic web resemblance to the neural networks found in the human brain. This powerful analogy has captured the imagination of not just scientists but philosophers as well. hinting that the universe might be organized in a way that resembles a colossal information processing system. Located at the intersections of this network are galactic clusters, all held together by gravity and orbiting a shared center of mass. Stretching between these hubs are what you could call galactic highways, filaments that channel matter from one area to another, feeding galaxies with the streams of gas and dark matter necessary for them to create new stars. What is truly astounding is that this cosmic web is still evolving. Driven by dark energy, the voids are expanding, causing the filaments to thin out as galaxies are pushed further apart. If this accelerated expansion continues, observers in the far future may see only their own isolated island of matter, cut off from the rest of the cosmos. Examining this structure provides crucial insights into how the earliest galaxies came into being. Light from distant quasars, as it travels through intergalactic gas, picks up an imprint of how matter was distributed in the young universe. By analyzing this light, astronomers can piece together a picture of the cosmic web at various stages of its history, much like looking through a photo album of the universe's life. It leads me to wonder if this gigantic network is more than a random arrangement of matter, perhaps reflecting fundamental laws we are only now beginning to understand. When you gaze at the stars and galaxies, it feels as though you are seeing the bulk of what the universe has to offer. In truth, however, all visible matter, everything that constitutes stars, planets, gas, and dust, makes up a mere 5% of the cosmos's total mass and energy. The rest is concealed from view, with the majority of this hidden component being dark matter, an enigmatic substance that doesn't emit or absorb light, and is consequently undetectable by any telescope. The existence of dark matter was inferred by scientists, not through direct observation, but by its powerful gravitational effects. Back in the 1930s, astronomer Fritz Zwicky observed that galaxies within clusters were moving far too quickly to be held together by their visible mass alone. A similar revelation came in the 1970s from Vera Rubin, who meticulously studied the rotational speeds of stars in galaxies and found that they defied the laws of physics. According to Newtonian principles, stars at a galaxy's edge should have moved much slower than those near the center, yet they were traveling at nearly the same speed. This anomaly could only be explained if a vast, invisible mass was distributed throughout the galaxy, providing the additional gravitational force needed to hold it together. Today you should understand that dark matter forms the essential scaffolding upon which galaxies and the entire cosmic web are constructed. Without it, the universe would be a profoundly different place. Without this strange substance, matter would never have been able to coalesce into the vast structures you see, such as galaxies and galactic clusters. But what exactly is it? Several compelling hypotheses exist, with one of the most prominent suggesting that dark matter is composed of undiscovered elementary particles called WIMPs, which stands for Weakly Interacting Massive Particles. These particles are thought to engage with ordinary matter almost exclusively through the force of gravity. Other scientists speculate that dark matter could consist of axions, which are hypothetical, extremely light particles believed to permeate the entire universe, like a vast, invisible wave. There are even more audacious theories, proposing that dark matter might be an artifact of hidden dimensions, or a manifestation of modified gravitational laws that we have yet to fully comprehend. Even though dark matter is unseen, you might be surprised to learn we can map its presence by observing how its gravity warps light from distant galaxies. This effect is known as gravitational lensing. As light journeys past a massive object, its trajectory is bent, and by analyzing this distortion, we can precisely calculate the location and quantity of dark matter. Unraveling the true nature of dark matter remains one of the greatest challenges in modern physics and astronomy, as its discovery doesn't just add to our model of the cosmos, it fundamentally transforms it. As you consider this before sleep, you can picture yourself surrounded by an ocean of unseen material, silently holding galaxies together with invisible threads that connect everything in existence. We are living within this enigma, and every new star you see outside your window is merely a tiny glimmer in an immense, concealed world. If you think of dark matter as the invisible scaffolding that holds galaxies together, then dark energy is the unseen force actively pushing them apart. It is now widely accepted as the primary driver behind the accelerating expansion of our universe. Until the close of the 20th century, the scientific consensus was that the cosmos, while expanding since the Big Bang, was gradually being slowed by the pull of gravity. However, a startling discovery was made in 1998 by two separate teams of astronomers observing faraway supernovae. The universe's expansion is not decelerating, but is actually speeding up. This revelation was a profound shock to the scientific community and prompted physicists to introduce the concept of dark energy. Current estimates suggest that dark energy constitutes about 68% of the universe's total mass and energy, pervading all of space and exerting a repulsive force, unlike gravity. While the exact mechanism behind its function is still a mystery, several hypotheses have been put forward. One theory connects dark energy to the cosmological constant, a concept Albert Einstein first proposed in his equations of general relativity, only to later label it his greatest mistake. This idea suggests that the energy of a vacuum, even in total emptiness, possesses a non-zero value that creates a pushing effect, driving galaxies away from one another. Another hypothesis proposes that dark energy is a unique field known as quintessence, which varies over time and could mean the universe's accelerating expansion might one day change or even reverse into a period of deceleration. More radical notions even suggest that dark energy is merely an illusion, a product of our flawed understanding of gravity on cosmological scales. The influence of dark energy on the ultimate fate of the universe is colossal. Should its properties remain constant, the cosmos will expand at an ever-increasing rate, eventually causing galaxies to become so distant that they will vanish from each other's view in a scenario known as the Big Rip. If dark energy were to strengthen, it could potentially rip apart galaxies, stars, planets, and even individual atoms. Conversely, if its influence wanes, gravity might reassert its dominance, causing the universe to contract in what is theorized as the Big Crunch. We do not yet know which of these futures will come to pass, but it's evident that dark energy is the key to deciphering the destiny of our entire cosmos. As you close your eyes, you can envision yourself within a vast sea of invisible force, gently, yet unceasingly carrying galaxies apart and widening the void between them. This movement is silent and infinite, destined to continue for billions of years after the last star has extinguished its light. If you could journey back in time 13.8 billion years, you would witness a universe in its infancy, only a few 100,000 years old. It was not a realm of stars and planets, but a dense, searing ocean of plasma filled with photons, electrons, and protons. In this state, light was trapped, unable to travel freely as it incessantly scattered off charged particles. But a crucial turning point arrived, an event scientists refer to as recombination. As the universe's temperature fell to around 3000 Kelvin, electrons and protons merged to create neutral hydrogen atoms, rendering space transparent to light for the first time. The photons released in that moment began their long journey, forming the first light we can ever observe, now known as the cosmic microwave background radiation. Today, this ancient light reaches us from every direction, bathing the entire sky in a faint microwave glow at a temperature of just 2.7 Kelvin, slightly above absolute zero. To the naked eye, this background radiation would appear perfectly uniform. However, ultra-sensitive instruments aboard satellites like COBE, WMAP, and Planck have detected incredibly small temperature fluctuations, variations of just thousandths of a degree. These tiny inconsistencies were the very seeds from which all future galaxies and stellar clusters would eventually sprout. Analyzing the cosmic microwave background is akin to reading an ancient scripture detailing the birth of the universe. Its patterns have allowed scientists to ascertain the universe's age, its elemental makeup, and its overall geometric structure. This relic radiation has revealed that the cosmos is composed of 5% ordinary matter, 27% dark matter, and 68% dark energy. Furthermore, it has confirmed that, on average, space is flat, and that our universe indeed began in the hot, dense state we call the Big Bang. Remarkably, you can even pick up this primordial light at home with an old analog television. When you notice the static, or snow, on a vacant channel, about 1% of that visual noise is actually the signal from the cosmic microwave background, a relic radiation that has journeyed across the cosmos for nearly 14 billion years. As you drift to sleep, considering this, you can picture yourself enveloped by the most ancient light in existence. This glow doesn't diminish. It streams silently across eons, a faint echo from the dawn of time, reminding you that we are all part of a grand narrative that started in a single, brilliant moment. When you consider gravity, your mind likely pictures the force holding you to the Earth or guiding planets in their orbits around stars. However, in Albert Einstein's theory of relativity, gravity is described not as a force, but as the warping of space-time caused by the presence of mass and energy. When truly massive objects accelerate or collide, this distortion can propagate across the universe in waves. These are not disturbances in air or water, but ripples in the fundamental fabric of reality itself, which are known as gravitational waves. Einstein first predicted that these waves must exist back in 1916, yet he doubted whether they could ever be detected because they are incredibly faint. For a gravitational wave to be observable, it must be generated by events of immense scale, such as the merging of black holes or the collision of neutron stars, which unleash an amount of energy comparable to the entire radiative output of the observable universe. For many years, gravitational waves were purely a theoretical concept. The first piece of indirect evidence appeared in 1975, when astrophysicists Russell Hulse and Joseph Taylor found a binary system of neutron stars whose orbit was steadily decaying. This orbital shrinkage perfectly matched Einstein's calculations, indicating the system was radiating energy away as gravitational waves. Still, it wasn't until 2015, almost a full century after the initial prediction, that a direct detection was made. The LIGO observatory's laser interferometers registered a subtle chirp, a signal from two black holes merging, 1.3 billion light-years from Earth, which caused space-time here to stretch and compress by less than the width of a proton. Today, gravitational waves have opened up an entirely new branch of astronomy. For centuries, you could only study the universe through light, across the spectrum from radio waves to gamma rays. Now, however, we can effectively listen to the cosmos by sensing the vibrations produced by its most violent events. We have already logged dozens of black hole and neutron star mergers, and these observations are even deepening our understanding of how heavy elements are forged as colliding neutron stars seed the universe with materials like gold and platinum. Looking ahead, as our detectors become even more sensitive, we might capture gravitational waves from the period of the Big Bang itself. This would be akin to hearing the opening moments of the universe's creation, offering an auditory complement to the visual information provided by the cosmic microwave background. Contemplating this as you fall asleep, you can imagine that the space around you is not perfectly still, but is constantly thrumming with the faint tremors of distant cosmic dramas, the subtle music of the universe that we are just learning to hear. Black holes rank among the most enigmatic and compelling objects known to exist. They are defined by their ability to trap everything, preventing even photons of light from escaping their grasp. This boundary is known as the event horizon, a threshold of no return. Anything that crosses it is forever lost to the black hole's interior. The concept of such an object actually dates back to the 18th century, when Jean-Michel and Pierre-Simon Laplace theorized that stars could be so massive that even light would be unable to escape their gravity. However, a true scientific understanding of these objects arrived with Albert Einstein's general theory of relativity in 1915. Shortly thereafter, Karl Schwarzschild derived the first exact mathematical solution from Einstein's equations, describing a spherical body with this kind of extreme gravitational pull. Black holes are found in various sizes, from stellar mass black holes, which form from the collapse of massive stars and are several times the mass of our Sun, to the supermassive black holes at the centers of galaxies, which can be millions or even billions of times more massive. The origin of these supermassive black holes remains one of the greatest unsolved puzzles in astrophysics, with leading hypotheses suggesting they either grew from the collapse of the universe's first gigantic stars, or formed through a rapid process of consuming matter and merging with other black holes. Paradoxically, despite being invisible themselves, black holes can be surrounded by some of the most luminous phenomena in the cosmos: accretion disks. These are turbulent whirlpools of superheated gas and dust that glow at millions of degrees as they spiral toward the event horizon, emitting intense radiation, particularly in the X-ray spectrum, which our space telescopes can observe. In 2019, humanity achieved a monumental feat by capturing the first direct image of a black hole, or more precisely, its shadow, at the heart of the galaxy M87, thanks to the coordinated efforts of the Event Horizon Telescope. This accomplishment served as a powerful confirmation of Einstein's theories and a landmark in our study of these cosmic mysteries. There are also more speculative theories proposing that a black hole could conceal a wormhole, a theoretical tunnel through spacetime. If true, falling into one might not be an act of annihilation, but a transition to a reality you cannot yet fathom. Although black holes are often portrayed as insatiable cosmic devourers, they are not nearly so aggressive in reality. A planet or star will orbit one without incident as long as it doesn't stray too close to the event horizon. Lying in the dark and picturing these silent sentinels of the cosmos, you can sense that they might be more than just symbols of an ultimate end. It's possible they represent gateways to something entirely new, something our imaginations have only just begun to touch. If you think of a black hole as a cosmic prison from which nothing can escape, then its theoretical counterpart, a white hole, is the complete opposite. A white hole is a hypothetical object that nothing can enter from the outside, but from which matter and energy are continuously ejected. You can visualize it as a fountain erupting from the fabric of space-time itself, endlessly spewing out its contents without ever taking anything in. This fascinating concept of white holes arose not from observation, but as a purely mathematical solution within Einstein's equations. While examining the equations that describe black holes, physicists uncovered a symmetrical solution in which time seemingly runs in reverse. Whereas everything within a black hole hurtles toward a central point, in a white hole, all matter would instead erupt outward. To date, no white hole has ever been directly observed, leading some scientists to argue that such objects are impossible, requiring physical conditions that are no longer present in our cosmos. Others, however, entertain the idea that white holes might indeed exist, though they would be exceptionally rare and fleeting phenomena. A more audacious hypothesis proposes that a white hole could be the outlet of a black hole, essentially the other end of a wormhole. In this model, any material that tumbles into a black hole in one corner of the universe might eventually be expelled from a white hole in a completely different area of space, or perhaps even in another dimension. Some researchers have gone so far as to theorize that our own Big Bang was the emergence of a colossal white hole, which would mean our universe is the product of matter and energy being ejected from another reality entirely. Another fascinating concept suggests that microscopic white holes could manifest as the final stage of a black hole's evaporation, a process outlined by Stephen Hawking's mechanism. At the conclusion of its existence, a black hole might violently flare up, casting out all its residual matter. For the time being, these are all theoretical constructs, yet exploring them enhances our comprehension of the cosmos's fundamental laws and the very limits of possibility. As you drift to sleep with this idea, you can picture a point in the universe's depths from which light and matter perpetually burst forth, a kind of cosmic exhalation that shapes the destiny of worlds, even though we can never draw it in. Neutron stars stand as some of the densest objects known, surpassed only by black holes. They are formed when a colossal star concludes its life in a supernova, an explosion that ejects the star's outer layers while its core collapses under its own immense gravity. The resulting pressure is so extreme that electrons and protons are forced to combine, creating neutrons, which culminates in a massive sphere of pure neutron matter. This material is so dense that just a single teaspoon of it would have a mass of billions of tons. Though diminutive by cosmic measures, typically around 20 kilometers in diameter, these stars possess a mass similar to our sun's. This incredible compactness grants them an extraordinarily powerful gravitational pull. Many neutron stars, known as pulsars, rotate at incredible velocities, sometimes hundreds of times per second, emitting focused beams of light or radio waves that appear as regular pulses when they sweep across our line of sight. Pulsars have proven to be indispensable instruments for astronomical study, enabling us to measure cosmic time with greater accuracy than atomic clocks, and even to detect gravitational waves. A unique subset of these objects, called magnetars, possess magnetic fields trillions of times more powerful than Earth's, capable of warping the very fabric of atoms. A single flare from a magnetar's surface can unleash more energy in a split second than our sun does in 100,000 years. What lies at the core of a neutron star remains a mystery, though some theories suggest the existence of a quark-gluon plasma, a state of matter thought to have existed only in the first moments after the Big Bang. When neutron stars exist in binary pairs, their eventual merger generates powerful gravitational waves and forges heavy elements like gold, platinum, and uranium, scattering them across space. It's quite possible that the precious metals on our world were created in the crucible of these cosmic collisions. Contemplating this as you fall asleep, you might envision a tiny, incredibly dense star spinning in the distant cosmos, its rhythmic pulse of light crossing the void. It's almost as if the universe is tapping on the window of our awareness, reminding you that even the most compact objects can hold a power that is truly without limits. Quasars are counted among the most luminous and energetic phenomena in the universe, with a brilliance so fierce it can overwhelm the light of entire galaxies. Their name, an abbreviation of quasi-stellar objects, comes from the fact that they initially appeared to be nothing more than ordinary stars. In truth, a quasar is the hyperactive nucleus of a faraway galaxy, fueled by a supermassive black hole at its center. As immense quantities of gas, dust, and even entire stars are drawn toward the galactic core, they form a swirling accretion disk around the black hole. Within this disk, the material is heated to billions of degrees, causing it to radiate a tremendous amount of energy across the entire electromagnetic spectrum, from radio waves to X-rays. Because quasars are situated billions of light years from us, we observe them as they were in the remote past, when the universe was in its infancy. The energy released by some quasars is equivalent to the luminosity of trillions of suns, and their powerful jets can slice through intergalactic space gas, serving as cosmic lighthouses. It's for this reason that astronomers refer to them as beacons of the distant universe. Quasars are remarkable not only for what they are, but for what they reveal about the space between them and us. By analyzing how their light is affected as it travels through cosmic clouds, scientists can map the composition of the intergalactic medium across eons of cosmic time. One prominent theory suggests that quasars were far more prevalent in the early universe, positing that every massive galaxy may have passed through an active quasar phase before its central black hole consumed all the nearby fuel and grew dormant. Some researchers even propose that quasars could be tied to events that unfolded shortly after the Big Bang, and that by studying them, we might gain insight into the enigmatic natures of dark energy and dark matter. As you fall asleep with this in mind, you can imagine an unbelievably bright fire blazing in the silent expanse of space, billions of light years away. A fire fed by matter spiraling into an endless abyss. This radiance has journeyed to us from the dawn of creation, softly gracing your eyes with a reminder that you are witnessing the lingering echoes of an ancient cosmic play that unfolds even now. Nebulae are immense interstellar clouds of gas and dust that can span for tens or even hundreds of light years. They manifest in various ways. Some blaze with brilliant colors, while others appear as dark shrouds, hiding the stars behind a thick veil of cosmic particles. Crucially, nebulae are more than just breathtaking celestial scenery. They are fundamental players in the life of the cosmos, as they serve as the very places where stars are both born and laid to rest. Among them are emission nebulae, which shine because of the energy from ionized gas, a glow often triggered when young, hot stars unleash ultraviolet radiation that excites the surrounding material. The Orion Nebula, a stellar nursery situated a mere 1,300 light-years away where new stars are currently forming, is a renowned illustration of this process. In contrast, reflection nebulae do not generate their own light. Instead, they scatter the light from nearby stars. These often take on a bluish hue, such as the haze enveloping the Pleiades star cluster. Dark nebulae, however, do the opposite by absorbing starlight, which creates enigmatic black figures against the luminous backdrop of the galaxy. A distinct classification is reserved for planetary nebulae, which are not cradles of new stars but rather the final testaments of stellar death. When a star comparable to our Sun runs out of fuel, it expels its outer layers, which expand into a cloud of gas lit up by the star's hot, dense core, what we call a white dwarf. Even more spectacular are the remnants of supernova nebulae, which result from the cataclysmic explosions of massive stars. The Crab Nebula, for instance, with its intricate filamentary structures, consists of the glowing debris from a star that erupted in the year 1054, an event that was documented by astronomers of that era. These celestial clouds are not passive decorations. They are active agents in the grand cosmic cycle. The very gas and dust cast off by dying stars provide the raw materials for subsequent generations of stars and their planetary systems. This means that the atoms of carbon, oxygen, and iron constituting your own body were once adrift within such formations. As you drift into sleep with these ideas, you can envision a massive cloud somewhere in the vastness of space, slowly coalescing, shaping the future stars, planets, and perhaps even life. A life that might, one day, turn its gaze to the night sky and recognize the nebula from which it emerged. Only a few decades ago, astronomers were limited to speculating whether other stars hosted their own families of planets. Now, we are aware of thousands of exoplanets, worlds that circle stars outside our solar system, and their numbers grow with new discoveries nearly every week. Their identification has been made possible by breakthroughs in telescope technology and innovative techniques that can spot the minuscule fluctuations in a star's brightness or movement caused by an orbiting planet. The most common of these are the transit method, which observes the slight dimming of a star as a planet crosses its face, and the radial velocity method, which detects the slight wobble in a star's position due to a planet's gravitational pull. It was the transit method that enabled the Kepler Space Telescope to find thousands of new worlds, demonstrating that planets are the norm, not the exception. The sheer variety of these exoplanets is astounding. There are hot Jupiters, which are giant gas worlds orbiting so close to their stars that their surface temperatures can soar above 1,000 degrees Celsius. You can also find super-Earths, which are rocky planets larger than our own, potentially harboring oceans that are hundreds of kilometers deep. Then, there are the truly strange worlds, where the weather might include rain of molten metal or glass, and the skies are painted in hues you could hardly imagine. Scientists are especially focused on planets located within the habitable zone, which is the orbital region around a star where conditions are right for liquid water to exist. a critical component for life as we understand it. Some of these potentially life-sustaining planets are only a few dozen light-years from us, which in cosmic terms is practically in our neighborhood. With every new finding, the probability increases that somewhere in the universe there are other worlds where life has taken hold. It's possible that somewhere out there, other civilizations are already looking up at their own star, pondering the very same questions that we do. Falling asleep with such thoughts, you might picture the night sky of another world, one illuminated by 2 or 3 suns, or adorned with rings that shimmer in the starlight, or with distant moons that glide slowly across the heavens. Although we cannot journey to them yet, the mere knowledge of their existence makes our universe feel infinitely more dynamic and mysterious. When we consider planets and moons, our minds typically conjure images of warm worlds with atmospheres and the potential for liquid water. However, both within our solar system and far beyond it, there exists a whole category of icy worlds, places that are frigid, yet not necessarily barren, and in some instances may even be habitable. This group includes the giant moons of the outer planets, like Jupiter's moon Europa, and Saturn's moon Enceladus, as well as Ganymede, Callisto, and even dwarf planets such as Pluto or Eris. The surfaces of these bodies are encased in thick ice, but beneath these frozen shells may lie vast, dark oceans of liquid water. This water remains liquid due to internal heat or the powerful tidal forces exerted by their parent planets. Europa is a particularly captivating object for astronomers. Under its icy crust, which is several kilometers thick, there is likely an ocean containing twice the volume of all the seas on Earth combined. On Enceladus, the Cassini spacecraft detected geysers erupting water vapor and organic molecules, the potential building blocks for life, directly into space. These frozen worlds serve as ancient time capsules, preserving the early history of our solar system. The thick ice on their surfaces acts as a shield, protecting their subsurface oceans from dangerous cosmic radiation and creating a stable environment that has persisted for billions of years. This implies that if life ever did emerge in these hidden oceans, it could have evolved in relative security, thriving in total darkness and drawing energy from chemical reactions instead of sunlight. But the allure of icy worlds extends beyond the search for life. They offer scientists invaluable insights into how planets form, how water and other vital substances were distributed throughout the early solar system, and even provide clues about the processes at work on distant exoplanets. Just imagine yourself standing on the surface of Europa. Imagine a black sky above you, where the colossal form of Jupiter slowly glides by, while miles of ice lie beneath your feet, concealing a turbulent, hidden ocean. In that profound darkness, life forms beyond our imagination could exist. Contemplating this as you drift to sleep reveals that these icy realms are not barren wastelands, but potential gateways to new biology and unwritten chapters in the saga of the universe. Back in 1916, Albert Einstein proposed that space and time were not a static stage for events, but a dynamic fabric, capable of being stretched, compressed, and warped by mass and energy. He theorized that monumental cataclysms, like the collision of black holes or neutron stars, would send faint ripples propagating through this fabric in every direction. We refer to these disturbances as gravitational waves. For many years, this concept was confined to a beautiful equation on paper, as the waves were considered so faint that their detection seemed impossible. However, a revolutionary event in 2015 changed astronomy forever. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first-ever detection of gravitational waves, which were generated by two black holes merging over 1 billion light-years from Earth, thus verifying one of the final, unproven tenets of relativity. Gravitational waves are distinct from light, radio signals, or particles. They are fundamental distortions in the universe's geometry that travel through everything unobstructed. When one of these waves arrives at Earth, it infinitesimally stretches and compresses space by an amount smaller than a proton's diameter. To capture such a minuscule effect, scientists have constructed enormous detectors that use lasers to measure distances with almost unimaginable precision. Today, gravitational waves provide us with a completely new method for observing the cosmos, allowing us to listen to cosmic events that are invisible to traditional telescopes. We can now identify the mergers of black holes that are undetectable in the electromagnetic spectrum, and even witness the creation of heavy elements during the collisions of neutron stars. Future space-based observatories, like the Laser Interferometer Space Antenna, or LISA, are designed to detect these waves with even greater sensitivity, potentially giving us insight into the universe's earliest moments, and perhaps the echo of the Big Bang itself. Falling asleep with this knowledge, you can envision the silent waves from distant cosmic disasters passing through your very body right now. While we cannot feel them, they carry with them the history of billions of years, much like the gentle, unseen breath of the universe, which is only perceptible to our most advanced instruments. When you gaze at the night sky, you might think you were seeing nearly everything that exists: the stars, planets, nebulae, and galaxies. The truth, however, is that all visible matter constitutes just a small fraction of the cosmos. The vast majority is concealed within what we call dark matter, an enigmatic substance we perceive only through its gravitational pull, not by direct observation. The discovery of dark matter originated from studying how galaxies move. In the 1930s, the astronomer Fritz Zwicky observed that galaxies within clusters were moving too rapidly to be held together by their visible mass alone. Decades later, Vera Rubin's work confirmed that stars in spiral galaxies rotate at consistent speeds, whether at the outer edges or near the center, an observation that is impossible to account for with only the matter we can see. The sole conclusion is that some unseen mass must be generating extra gravity. This substance doesn't emit or reflect light and has no interaction with electromagnetic radiation. Yet its gravitational force is what prevents galaxies from flying apart and shapes the vast structure of the universe. Scientists theorize that dark matter could be composed of undiscovered elementary particles, such as weakly interacting massive particles, or WIMPs, and axions, which have minimal interaction with ordinary matter. Despite decades of searching, none of these proposed particles have ever been directly detected. Yet dark matter's role in the evolution of the cosmos is fundamental. Without its influence, galaxies and stars might never have come into being. Computer simulations suggest that its invisible filaments formed the scaffold upon which the entire visible universe was constructed. There are even more audacious theories, such as the idea that dark matter is made of miniature black holes that formed right after the Big Bang. If this is correct, we are surrounded by the most ancient objects in existence, predating even the first stars and galaxies. Drifting to sleep with this thought, you can picture everything we see as mere islands of light in a vast, invisible ocean, hoping that one day we will uncover what lies in the darkness that holds our universe together. While dark matter attracts and binds galaxies, dark energy accomplishes the exact opposite. It pushes space apart, driving the accelerating expansion of the universe. This discovery stands as one of the most perplexing and profound in modern cosmology, completely reshaping our perception of the cosmos. Until the late 20th century, the scientific consensus was that gravity would gradually slow the universe's expansion following the Big Bang. However, in 1998, two separate teams of astronomers studying distant supernovae found something entirely unexpected. The expansion rate isn't slowing down. It's actually speeding up. This observation required the introduction of a new cosmic component to explain it: dark energy. We now understand that this mysterious force accounts for roughly 70% of all mass and energy in the universe, though its true nature remains an enigma. One leading hypothesis is that dark energy is an intrinsic property of space itself, a concept known as the cosmological constant, which Einstein once added to his equations only to later call it his greatest blunder. An alternative theory posits that dark energy is a dynamic field that fluctuates over time, akin to a quantum ether. Its influence can be visualized as an invisible, anti-gravitational pressure that continuously stretches the very fabric of space-time. As the fabric of space stretches, it seems to generate more dark energy, which in turn fuels an ever-quickening rate of expansion. This self-perpetuating cycle points toward some startling possibilities for the far future, as galaxies will eventually recede from one another until they vanish from sight. A more extreme outcome is the theoretical Big Rip, where cosmic expansion accelerates so violently that it dismantles galaxies, stars, and even the atoms you are made of. It is a profound mystery to us, a force whose existence we have only just begun to acknowledge, leaving one to imagine the universe as a silent, expanding ocean, pulling all its shores, and all of us, apart. At one time, our entire universe was contained in a state of unimaginable heat and density. Roughly 380,000 years after the Big Bang, conditions cooled sufficiently for atoms to coalesce, which finally allowed light to travel freely through space. We call this primordial glow the cosmic microwave background, or CMB, and it represents the most ancient form of electromagnetic radiation that our instruments can possibly detect. It permeates the cosmos, arriving from every conceivable direction as a faint echo of creation, discovered entirely by chance in 1965 when two researchers, Arno Penzias and Robert Wilson, detected a persistent background hiss in their radio receiver that was this very light from the dawn of time. This CMB is now our single most valuable source of data about the early cosmos, revealing minute temperature variations, known as anisotropies, when studied with precise instruments. These almost imperceptible differences in heat correspond to the initial distribution of matter moments after the Big Bang, acting as the seeds from which all galaxies and stars would eventually grow. By analyzing the cosmic microwave background, scientists have calculated the universe's age at approximately 13.8 billion years, and determined its composition to be about 5% ordinary matter, 27% dark matter, and 68% dark energy. Each photon of this light has journeyed for nearly 14 billion years to reach you, a poetic reminder that you are constantly surrounded by an invisible, ancient glow, telling the story of how everything began. Our discussions of the cosmos often dwell on its origins, but this naturally leads you to ask about its ultimate conclusion. Scientists have outlined several potential endgames for the universe, each as captivating as it is unnerving. The most widely accepted theory is the heat death, where dark energy drives unending expansion until all stars have extinguished and only cold, dark remnants float in an empty void. A more explosive, though less probable alternative is the Big Rip, where dark energy's influence grows so strong that it tears apart the very structure of matter. Conversely, if gravity were to regain dominance, the universe could face a Big Crunch, collapsing back into a super-dense point, perhaps to trigger a new Big Bang. Beyond these possibilities lie even more speculative concepts, like the Big Bounce, a theory suggesting that the universe cycles endlessly through expansion and contraction. Another is the multiverse hypothesis, which posits that our cosmos is just one among countless others, making its eventual end a minor event on an infinite stage. No matter which fate awaits, you and I exist in the present, a remarkable time when we can still observe the stars and seek to understand our place among them. Perhaps contemplating the universe's destiny can deepen our appreciation for this brief moment, a time when our cosmos is still vibrant and filled with light. When you hear the word cosmos, the image that likely springs to mind is a deep, dark expanse sprinkled with the brilliant lights of countless stars. While this picture has captivated humanity for millennia, the underlying reality is vastly more intricate. The universe is not merely a collection of celestial bodies separated by emptiness. It is a complex tapestry woven with invisible forces and phenomena that we are just starting to map. The truth is, what you can perceive with your own senses is an astonishingly small slice of what actually exists. Your vision is confined to a slim band of the electromagnetic spectrum, and you remain blind to the immense wealth of information carried by infrared, ultraviolet, radio waves, and gamma rays, the very wavelengths that hold the deepest secrets of our universe. You might find it fascinating that many stars that look dim to our eyes are actually radiant in the infrared spectrum, while others, practically unseen, are potent sources of X-rays. These emissions often signal the remnants of supernovae, or the energetic cores of distant galaxies, where matter plunges into a black hole and is heated to billions of degrees. While you cannot witness these cosmic events directly, we can perceive them by using specialized instruments that convert these signals into ranges our senses can interpret. Even the blackness of space itself is not an absolute void, as it is populated by clouds of interstellar gas and dust between the stars and galaxies. A single cubic meter might contain just a handful of atoms, yet this profound vacuum is capable of absorbing, reflecting, or scattering light. Over immense stretches of time, these very clouds transform into stellar nurseries, eventually collapsing under their own gravity to form new stars. The cosmos is a place of perpetual motion, where stars are born and subsequently perish, galaxies collide, and planets can be ejected from their orbits. Black holes actively consume surrounding matter, unleashing tremendous jets of energy in the process. While we tend to perceive these phenomena as incredibly slow, the universe operates on a different time scale. Events spanning millions of years are but fleeting moments on a cosmic scale. There is another remarkable aspect to our observation. We are always viewing the cosmos as it existed in the past. It takes 8 minutes for light from the sun to reach us, 4 years from the closest star, and billions of years from the most distant galaxies. This reality means that when you gaze at the night sky, you are effectively flipping through a colossal photo album documenting the universe's long history. In this lecture, I will guide you step by step through some of the most astounding phenomena and enigmas of the cosmos. We will delve into topics like dark matter and dark energy, the life and death of stars, and the formation of planets, exploring how the universe is fundamentally connected to each of us. You will come to understand that this seemingly endless darkness is, in truth, brimming with light that our eyes simply cannot see. When you contemplate the cosmos, the image of a frigid vacuum often comes to mind, a place without air or warmth, with temperatures approaching absolute zero. While this is partially accurate, the cosmos is far from being uniformly cold. It is a realm where zones chilled to near absolute zero exist alongside regions heated to tens of millions of degrees. This paradox may sound unbelievable, but it is governed by the laws of physics, not by anything mystical. The average temperature of the vast expanse of intergalactic space is approximately 2.7 Kelvin, which is about 273 degrees Fahrenheit, 0.15 degrees below 0 Celsius. This pervasive cold is the cosmic microwave background radiation, a faint thermal echo from the Big Bang that fills the entire universe. It radiates uniformly from every direction, acting as a constant reminder of the moment, around 380,000 years after its inception, when the cosmos first became transparent to light. However, if you were to shift your focus to a region of active star formation or near a supermassive black hole, the temperature would skyrocket to extraordinary levels. For instance, our Sun's surface is about 5,500 degrees Celsius, but its corona, or outer atmosphere, can reach a staggering 1 to 2 million degrees. This incredible heating effect still awaits a complete explanation, although scientists theorize it is linked to powerful magnetic fields, accelerating charged particles to immense velocities. Extremely hot environments are found elsewhere in space as well. Near stellar explosions known as supernovae, temperatures can surge to hundreds of millions of degrees. These cataclysmic events don't just obliterate stars. They also disseminate heavy elements into the cosmos, which are essential for the formation of planets, atmospheres, and ultimately, life itself. Conversely, some locations in the universe are even colder than the cosmic average. The Boomerang Nebula, situated roughly 5,000 light-years away from Earth, registers a temperature of just 1 Kelvin, a state that is almost absolute zero. This extreme chill is created when gas ejected by a dying star expands rapidly, causing it to lose energy much faster than it can absorb it from the cosmic background radiation. It's crucial to recognize that temperature in the vacuum of space isn't experienced in the same way as on Earth. It is a measure of the energy of individual particles, not the ambient warmth you might feel. You could actually freeze in a region with million-degree temperatures, because the matter is so sparse that a negligible amount of heat would ever be transferred to your body. This dramatic contrast between extreme cold and intense heat is what drives the unique dynamics of the universe. The coldest regions become the birthplaces of stars, as gravity compresses gas clouds until nuclear fusion ignites. Hot zones, on the other hand, frequently signal the end of a star's life cycle, when it explodes and incinerates everything in its vicinity. The cosmos, therefore, is not merely a dark and cold expanse. It is a grand tapestry, woven with icy nebulae, blazing gas clouds, serene intergalactic voids, and violent stellar catastrophes. When you look up at the night sky, you perceive what appears to be a great dome dotted with innumerable stars. But what you're actually seeing is an abyss of both space and time. Every single point of light that reaches your eyes is not a present event, but rather something that transpired long ago. In this sense, we are all readers of a history book whose pages are written in light. The speed of light is finite, traveling at about 300,000 kilometers per second. While that seems incredibly fast by terrestrial standards, it is relatively slow across cosmic distances. The light from our sun takes roughly 8 minutes and 20 seconds to arrive at Earth, meaning we perpetually see it as it was 8 minutes in the past. Light from Proxima Centauri, our nearest stellar neighbor, journeys for over 4 years, while the Andromeda Galaxy appears to us as it did 2.5 million years ago. Advanced instruments like the James Webb Space Telescope and the celebrated Hubble Space Telescope empower us to peer even deeper into this cosmic history. Scientists are now capable of observing light that has traveled for more than 13 billion years to reach us. This allows you to see objects as they existed shortly after the Big Bang, during an era when the universe was merely a few 100 million years old. You've likely heard of the cosmological horizon, which marks the absolute limit of what we can observe in the cosmos. This boundary is directly linked to the universe's age of approximately 13.8 billion years, as light from anything more distant simply hasn't had the time to reach us yet. However, because space itself has been expanding, the very objects we now see at that edge are actually located about 46 billion light-years from us today. When you peer that far into space and time, you don't find the well-defined spiral galaxies we're used to seeing. Instead, you witness the universe in its infancy. Small, faint, and chaotic collections of light that are the very first galaxies beginning to form. You are effectively watching the birth of the first stars as gravity slowly condenses scattered clouds of hydrogen into massive celestial bodies that would go on to illuminate and transform the cosmos with their energy. By examining these remote objects, you are doing more than just observing them. You are delving into the mechanics of cosmic evolution. We can see that these early galaxies were deficient in heavy elements, as those materials had not yet been forged within the cores of stars. Over vast stretches of time, as stars perished in supernova explosions, they enriched the universe with the very elements that, billions of years later, would coalesce to form planets and give rise to life. By examining these remote objects, you are doing more than just observing them. You are delving into the mechanics of cosmic evolution. We can see that these early galaxies were deficient in heavy elements, as those materials had not yet been forged within the cores of stars. Over vast stretches of time, as stars perished in supernova explosions, they enriched the universe with the very elements that, billions of years later, would coalesce to form planets and give rise to life. There is a certain philosophical depth to this realization. As you gaze toward the far reaches of the universe, you become a witness to events that unfolded not just before Earth came to be, but before our own sun ignited. You are observing light that has journeyed across space-time for billions of years just to enter a telescope's lens or strike your retina. It's a humbling thought that perhaps, on the other side of the cosmos, an observer looking our way right now would see Earth as it was when dinosaurs still walked its surface. If you could somehow perceive the cosmos not with your eyes but through the force of gravity, you would find that everything we typically think of as the universe, the stars, planets, nebulae, and galaxies, constitutes only a minuscule portion of a much grander structure. It turns out that all this visible matter makes up a mere 5% of the universe's total mass and energy, with the rest remaining completely hidden from our view. Of this unseen majority, roughly 27% is composed of dark matter, while the remaining 68% is attributed to dark energy. But what exactly is this dark matter, and what makes it so fundamentally important? It is a substance that does not emit, absorb, or reflect any light, rendering it entirely transparent to every form of electromagnetic radiation. Consequently, we are unable to observe it directly, though we are certain of its existence due to its powerful gravitational effects. The search for this substance began in the 1930s, when the Swiss-American astronomer Fritz Zwicky was studying a galactic cluster in the Coma Berenices constellation. He observed that the galaxies within the cluster were moving at such extreme velocities that they ought to have flung themselves apart if only their visible matter was holding them together. This led him to conclude that an immense quantity of unseen mass must be present, which he termed dunkle materiae, or dark matter. Further evidence emerged in the 1950s when the American astronomer Vera Rubin analyzed the rotational speeds of spiral galaxies. She confirmed that stars on the periphery of these galaxies orbit at the same velocity as those nearer the center, a phenomenon that is physically impossible if the galaxy's mass consists solely of its visible stars and gas. This discovery demonstrated that every galaxy must be enveloped in a vast halo of dark matter, possessing a mass several times greater than all of its visible components combined. Today, we find indirect proof of dark matter's existence everywhere we look. We see it in the phenomenon of gravitational lensing, where the light from distant galaxies is bent by the gravity of invisible mass concentrations. Its influence is also imprinted on the cosmic microwave background, the afterglow of the Big Bang, where tiny temperature fluctuations mirror the presence of this unseen mass in the universe's foundational structure. In fact, it was dark matter that provided the gravitational skeleton upon which galaxies first began to form. Several theories attempt to explain what dark matter could be composed of. One popular idea is WIMPs, which stands for weakly interacting massive particles, that would only rarely interact with ordinary matter. Another candidate is axions, hypothetical light particles that might pervade the cosmos. A third possibility is sterile neutrinos, a type of neutrino that interacts with other matter only through gravity. Despite building incredibly sophisticated detectors to capture even a single one of these particles, scientists have so far been unsuccessful. This lack of direct detection, however, doesn't mean it isn't real. In fact, without dark matter, we would be unable to explain why galaxies don't fly apart, or why the cosmos has the large-scale structure we observe. Dark matter truly is the foundational material upon which all of cosmic architecture is constructed. It may be invisible, but it dictates where and how galaxies, stars, and planets take shape. Without it, our own existence might not have been possible. This leads us to one of the most profound puzzles of our time. We live in a reality where most of what exists is invisible. Yet everything we can see depends on it. If dark matter serves as the cosmic adhesive that binds galaxies and their clusters, then dark energy is its complete opposite, a force that actively drives them apart. This force is responsible for the fact that the universe isn't just expanding, but that its expansion is accelerating. Up until the close of the 20th century, the prevailing scientific belief was that the universe's expansion, initiated by the Big Bang, should be gradually slowing down. The immense gravitational pull from all the stars, planets, gas, and even dark matter was expected to act as a brake on this process. But in the late 1990s, two separate teams of astronomers studying distant Type 1a supernovae, exploding stars with a predictable level of brightness, found that these cosmic beacons were dimmer than anticipated, meaning they were much farther away than calculations predicted. The only possible conclusion from this data was utterly shocking. The universe's expansion is not slowing down. It is actually speeding up. To account for this unexpected acceleration, scientists proposed the existence of dark energy. To this day, we do not know its true nature. It could be an inherent property of space itself, an idea Albert Einstein once called the cosmological constant. Or it might be the effect of a dynamic field, such as a hypothetical force known as quintessence. Presently, our best understanding is that dark energy constitutes about 68% of the universe's total mass energy, which means nearly 3/4 of reality is made of a substance we are almost completely ignorant about. We witness its influence in the rapid recession of galaxies at the observable universe's edge. This phenomenon isn't about galaxies hurtling through space, but rather the very fabric of space-time expanding between them, causing more distant objects to move away from us at ever-increasing speeds. One compelling hypothesis regarding the future suggests that if this accelerated expansion continues unabated, then, in billions of years, the vast majority of galaxies will vanish from our sight. They will cross our cosmological horizon, their light no longer able to reach Earth, leaving a future observer in a universe that appears dark and desolate, save for the few nearby galaxies gravitationally bound to our own. More dramatic fates are also possible, such as the Big Rip hypothesis, which proposes that dark energy could grow stronger over time. In this scenario, tens of billions of years from now, it would not only separate galaxies, but proceed to tear apart star systems, planets, and eventually, the very atoms that comprise matter. Milder alternatives exist, where dark energy might weaken or disappear, potentially triggering a big crunch in which the universe reverses its expansion and collapses back in on itself. The fundamental difficulty is our current inability to study dark energy directly. We can only infer its properties by observing its effects and creating models. As is often the case in science, the more we uncover, the more profound the questions become. Dark energy holds the secret to the universe's ultimate destiny. But for now, that secret is locked away, and we are only just beginning to search for the right key. I want you to imagine being in an immense auditorium just after a deafening sound has ceased, where faint reverberations still hang in the air. Our universe experienced something similar. Billions of years after the Big Bang, we can still detect its faint afterglow with our instruments, an echo known as the cosmic microwave background, or CMB. This radiation was first predicted in the 1940s by scientists who reasoned that if the cosmos began as an intensely hot and dense state, its initial light should still exist, stretched by cosmic expansion into a uniform low-energy thermal glow filling all of space. Its discovery was an accident that occurred in 1965, thanks to American engineers Arno Penzias and Robert Wilson. While trying to troubleshoot a persistent hiss in their radio telescope, and after ruling out every possible source of interference, they realized the noise was a constant signal coming from every direction in the sky. This was the moment humanity first directly detected the remnant echo of the Big Bang. The temperature of the CMB is incredibly low, approximately 2.725 Kelvin, which is just above absolute zero, or -173.15 degrees Celsius. This faint warmth is a relic from when the universe was only about 387,000 years old. Before that time, the cosmos was a dense, opaque plasma where photons were constantly scattered. Only when it cooled enough for atoms to form did light become free to travel unimpeded, and we are still seeing that ancient light today. Modern satellites, including COBE, WMAP, and Planck, have meticulously mapped the CMB, discovering that it is not perfectly uniform. It contains minuscule temperature variations, differences of mere millionths of a degree, that served as the primordial seeds for the formation of galaxies, stars, and planets. By analyzing this relic radiation, we have determined the universe's age, geometry, and composition, making it one of the strongest pillars of evidence for the Big Bang theory. Beyond established cosmology, the CMB inspires some truly fascinating speculation. Certain physicists theorize that its structure might contain faint imprints from ancient collisions between our universe and others, should a multiverse exist. Meanwhile, others scrutinize it for signs of primeval gravitational waves generated in the first moments of creation. In every sense, the cosmic microwave background provides us with a portrait of the universe in its infancy. This background radiation shows us what the cosmos was like before any stars, planets, or galaxies had ever formed. As you drift off to sleep, consider that in every direction you look, light is arriving that has been traveling for nearly 14 billion years. It is a profound reminder that we are all participants in an immense ancient story, whose pages we are just beginning to decipher. Hidden within the cold, dark expanses of interstellar space are enormous clouds of gas and dust. Though they may appear motionless and void of life, these regions are precisely where the magnificent and crucial event of starbirth takes place. Known as stellar nurseries or molecular clouds, their temperatures drop to just a few tens of degrees above absolute zero, allowing matter to become dense enough for gravity to take command. All it takes is a slight disturbance, perhaps from a nearby supernova's shock wave, for gravity to initiate the collapse of a region within such a cloud. As this dense clump contracts over millions of years, its core grows progressively hotter. Eventually, when the core's temperature reaches about 10 million degrees, thermonuclear fusion ignites. Hydrogen nuclei begin to merge into helium, releasing a tremendous amount of energy. And with that, a star is born, an object astronomers in this early phase call a protostar. The young star finds itself enveloped by a thick, swirling disk of gas and dust, setting the stage for an entirely new saga: the birth of planets. Within this disk, particles of dust crash into one another, merging to create progressively larger objects. This growth scales up from minute pebbles to planetesimals measuring tens of kilometers across, which then evolve into planetary embryos that gravitationally pull in even more matter, until they mature into complete planets. A planet's ultimate destiny is determined by its birthplace within this protoplanetary disk. In the hotter regions closer to the star, rocky worlds, such as Earth, Mars, or Venus, are the most likely outcome. Conversely, in the frigid outer reaches, planets can gather vast quantities of ice and gas, transforming into colossal giants like Jupiter or Saturn. This formation process is more than just a magnificent cosmic event. It holds the very key to our own origins, as our sun and its planetary system were born through this exact mechanism, roughly 4 billion years ago. The sequence began with a frigid cloud of gas, followed by the brilliant ignition of a new star, and culminated in the gradual assembly of planets, moons, asteroids, and comets. It's fascinating to realize that the majority of stars are not solitary creations, but emerge in large communities known as star clusters. While some of these stars eventually wander away, many stay bound together for billions of years, implying that somewhere in the universe, our sun has siblings that were forged from the very same cosmic cloud. To witness this cosmic genesis, scientists rely on radio telescopes and infrared observatories, which can peer through the dense dust clouds that typically conceal young stars from view. The James Webb Space Telescope has provided breathtaking glimpses into these stellar nurseries, capturing incredible images of immense pillars and swirling nebulae, where the next generation of stars is igniting. When you contemplate this before drifting off to sleep, you might feel a profound sense of tranquility, because we are composed of the very same atoms that were forged in the fiery cores of stars long ago. You are, quite literally, a child of the cosmos, and gazing at the night sky is like looking back at your own distant ancestral home. Much like living organisms, stars have distinct life cycles, beginning with their birth in cold gas clouds, and concluding with an end that could be a gentle dimming or a violent, catastrophic blast. A star's lifespan is dictated almost entirely by its mass. The larger it is, the more rapidly it consumes its fuel, leading to a much shorter existence. Our sun, being a star of average size, is expected to live for approximately 10 billion years, and is presently about 4 to 5 billion years into its life, residing in a stable period called the main sequence. During this phase, thermonuclear reactions in its core steadily convert hydrogen into helium, generating the outward energy that counteracts the inward pull of gravity. In stark contrast, stars that are dozens of times more massive than our sun have incredibly brief lives, lasting only a few million years as their cores burn through fuel at a furious pace. At the other end of the spectrum, small red dwarfs can persist for hundreds of billions of years, shining with a faint, steady light and undergoing very little change. Once the hydrogen fuel in a star's core is depleted, it enters a new stage of its evolution. The star swells dramatically to become a red giant, with its outer layers cooling even as its core shrinks and intensifies in heat. This allows for the fusion of helium into heavier elements, such as carbon and oxygen. For particularly massive stars, this elemental synthesis progresses even further, forging elements all the way up to iron. At this point, a fundamental principle of astrophysics takes over. Creating elements heavier than iron consumes energy, rather than releasing it. As iron builds up in the core of a massive star, fusion ceases, and the star can no longer support itself against its own immense gravity. The resulting collapse initiates one of the most spectacular events in the cosmos, a supernova explosion. The power of a supernova is staggering. In a matter of seconds, it unleashes more energy than our sun will produce over its entire multi-billion-year lifespan. These cosmic detonations are the crucibles where heavy elements like gold, platinum, and uranium are created, and then flung across space, becoming the raw ingredients for the next generation of planets and life. The destiny of the stellar remnant is determined by its mass. If the core weighs less than roughly 3 times the mass of our sun, it will crush down into a neutron star, an object of unimaginable density. Should the core's mass exceed this limit, gravity's victory is absolute, and the remnant collapses into a black hole from which nothing can break free. Stars comparable to our Sun experience a more serene end. After casting off their outer envelopes, they form a stunning structure known as a planetary nebula, while the core becomes a white dwarf, a searingly hot ember that will slowly cool and fade over billions of years. Every star you see is far more than a simple point of light. It's a cosmic forge that creates the very substance from which you and your world are made. Whenever you gaze up at them, you are witnessing not just their current state, but also the promise of new worlds that will one day be built from their ashes. If you think of stars as individual homes, then galaxies are like sprawling metropolises, populated with billions or even trillions of stars, vast clouds of gas and dust, and the enigmatic presence of dark matter. These colossal structures drift through the infinite universe like immense, self-contained islands, and each one is entirely unique. Our home galaxy, the Milky Way, is a spiral system that stretches about 100,000 light-years from end to end, and holds over 200 billion stars. Yet on a cosmic scale, it's hardly the biggest. Some galaxies are dozens of times larger in both size and mass. For instance, the mammoth elliptical galaxy IC 1101 spans over 6 million light-years and is estimated to contain as many as 100 trillion stars. Astronomers classify galaxies into several primary categories. You have spiral galaxies, like our Milky Way or Andromeda, with graceful arms where star formation is vibrant. Elliptical galaxies, which are typically older, more sedate collections of reddish stars. And irregular galaxies, which have chaotic shapes often resulting from galactic collisions. Galaxies seldom exist in complete isolation. They are gravitationally bound into groups, clusters, and even larger structures called superclusters. To give you a local example, our Milky Way belongs to the local group, a collection of roughly 50 galaxies that includes the Great Andromeda Galaxy and numerous smaller dwarf galaxies that orbit their larger neighbors. Imagine that these galactic clusters are themselves interconnected, forming a vast cosmic web. This structure is a network of dark matter filaments with clusters of galaxies at its intersections, separated by immense, nearly empty regions we call voids. If you could zoom out billions of light-years from our own galaxy, you wouldn't see a random scattering of light. Instead, your view would be of an astonishingly ordered structure, resembling a gigantic web woven from the finest threads that connect enormous hubs of matter. Galaxies, you see, do not drift in silent isolation. They constantly interact with one another through gravity, sometimes leading to direct collisions. When galaxies collide, it doesn't involve stars crashing into each other, as the distances between them are simply too immense. Rather, the powerful force of gravity orchestrates a grand reshaping of their entire structures, which can trigger fresh waves of star formation and completely transform their appearance. In fact, our own Milky Way is on a collision course with the Andromeda Galaxy, and in about 4 billion years, they will merge to create a new, giant elliptical galaxy that astronomers have preemptively named Milkomeda. At the heart of nearly every major galaxy, including our own, lurks a supermassive black hole. Ours is called Sagittarius A star, and it possesses a mass 4 million times greater than our Sun, playing a crucial role in the galaxy's evolution by governing star formation and shaping the distribution of matter. Contemplating this as you drift off to sleep, it's easy to feel as though you live in just one of trillions of cosmic cities. In this vision, every star is a sun, potentially with its own system of planets, and each galaxy represents a mere speck within a universe that stretches beyond all comprehension. The threads of this cosmic web are composed of galaxies, gas, and dark matter, and can extend for hundreds of millions of light-years, while the voids between them can surpass the size of thousands of galaxies combined. This entire structure is the direct result of how matter was distributed in the moments following the Big Bang, and the subsequent way gravity gathered it into denser regions over eons. Fascinatingly, sophisticated computer models like the Millennium simulation have revealed that the cosmic web bears a striking resemblance to the neural networks found in the human brain. This powerful analogy has captured the imagination of not just scientists, but also philosophers, hinting that the universe may be organized like an enormous information processing system. The nodes of this incredible network are gravitationally bound clusters of galaxies, all rotating around a common center of mass. Stretching between these nodes are what you could think of as galactic highways, filaments that channel streams of gas and dark matter from one region to another. These flows act as a vital nutrient source for galaxies, providing the raw materials they need to form new stars. What is particularly astounding is that this cosmic web is still evolving. Driven by the mysterious force of dark energy, the voids are expanding, causing the filaments to stretch and grow thinner as galaxies are pushed further apart. If this accelerated expansion continues, observers in the very distant future might see only their own small island of matter, completely cut off from the rest of the cosmos. Studying this structure provides profound insights into how the earliest galaxies came into being. Light from ancient, distant quasars passes through intergalactic gas, and in doing so, it picks up an imprint of how matter was arranged in the early universe. By analyzing this light, astronomers can reconstruct the cosmic web at various stages of its history, almost like flipping through a photo album of the universe's life. When you gaze at the stars and galaxies, it may seem like you're observing most of what the universe has to offer. In truth, all of this visible matter, everything from stars and planets to gas and dust, constitutes only about 5% of the total mass and energy in the cosmos. The remaining portion is hidden from us, and the majority of this concealed component is dark matter, an enigmatic substance that does not emit or absorb light, rendering it completely invisible to our telescopes. Scientists first inferred the existence of dark matter not through direct observation, but by witnessing its powerful gravitational effects on the things we can see. As far back as the 1930s, the astronomer Fritz Zwicky noticed that galaxies within clusters were moving far too quickly to be held together by their visible mass alone. A similar puzzle was uncovered in the 1970s by Vera Rubin, who found that stars on the outer edges of galaxies were rotating at nearly the same speed as those near the center, defying the predictions of Newtonian physics. This unexpected behavior meant that a vast, unseen mass must be distributed throughout each galaxy, providing the extra gravitational pull needed to hold it all together. Today, we understand that dark matter forms a kind of foundational framework upon which the entire cosmic web is built. Without it, the universe would be a very different place, as ordinary matter would never have been able to coalesce into the large-scale structures we see today. So, what exactly is this mysterious substance? There are several leading theories, with one of the most prominent suggesting it is composed of undiscovered elementary particles called WIMPs, or weakly interacting massive particles, that interact with normal matter only through gravity. Other hypotheses propose that dark matter could be made of axions, theoretical ultralight particles that might permeate the universe like an invisible field, while even more daring ideas suggest it could be a manifestation of hidden dimensions, or evidence that our current laws of gravity are incomplete. Remarkably, even though dark matter is undetectable by conventional means, you can chart its presence by seeing how it warps the light from far-off galaxies. This effect is known as gravitational lensing. As light journeys past any object with substantial mass, its trajectory is bent, and by analyzing this distortion we can deduce the location and amount of dark matter responsible for it. Figuring out the true nature of dark matter represents one of the greatest challenges in contemporary physics and astronomy, because it doesn't merely add to our understanding of the world, it fundamentally rewrites it. As you drift to sleep considering this, it's easy to picture yourself immersed in an ocean of invisible substance, which silently holds galaxies together, like unseen threads weaving through the cosmos. You and I exist within this enigma, where every new star you see is just a tiny point of light in an immense concealed reality. If dark matter serves as the cosmic cement binding galaxies, then dark energy is its direct opposite, a force that actively pushes them apart. This force is the very reason the universe's expansion isn't just ongoing, but is actually accelerating. This revelation stands as one of the most surprising and poorly understood cosmological discoveries of the past few decades. Up until the close of the 20th century, the scientific consensus was that the universe's expansion should be slowing down in the aftermath of the Big Bang. The collective gravitational pull from all stars, planets, gas, and even dark matter was expected to gradually apply the brakes to this process. However, in the late 1990s, two separate teams of astronomers observed distant Type 1a supernovae, exploding stars of a known brightness, and found they were dimmer than anticipated, which meant they were much farther away than our models predicted. The implication was staggering. The universe isn't slowing down at all. It's speeding up. To account for this acceleration, scientists put forward the concept of dark energy, though we still don't know what it is. It might be an intrinsic quality of space itself, referred to as the cosmological constant, an idea originally conceived by Albert Einstein. Or perhaps it's the result of a dynamic energy field, like the theoretical quintessence. The current belief is that dark energy comprises about 68% of the universe's total mass energy, meaning nearly 3/4 of your world is made of something completely unknown to us. We witness its influence in the observation that galaxies on the periphery of the known universe are retreating from us at incredible velocities. What's more, the farther away a celestial object is, the faster its recession. This isn't because galaxies are hurtling through space, but because the very fabric of space between them is stretching and expanding. One compelling hypothesis about the future suggests that if this accelerated expansion continues unchecked, in many billions of years, you will no longer be able to see most other galaxies. They will have receded beyond our cosmological horizon, with their light never able to reach Earth again, leaving the universe apparently dark and desolate for any future observer. More sensational scenarios also exist, such as the Big Rip theory, which posits that dark energy could strengthen over time, eventually tearing apart not just galaxies and solar systems, but planets, and even individual atoms tens of billions of years from now. Of course, there are less extreme possibilities. Dark energy's influence could wane, causing the expansion to slow or even halt, which could lead to an entirely different outcome like a big crunch, where the universe collapses back in on itself. The core issue is that we currently don't possess the technology to examine dark energy directly. We can only infer its properties from its effects and create theoretical models. As is often the case in science, the more you learn, the more you realize you don't know. Dark energy likely holds the secret to the ultimate fate of the universe. But for now, that secret is locked away, and we are just beginning to figure out how to find the keyhole. If you could journey back in time 13.8 billion years, you would find yourself in a very young universe, just a few 100,000 years old. This early cosmos wasn't filled with stars and planets, but was instead a dense, searingly hot soup of plasma, made of photons, electrons, and protons. In this opaque state, light was trapped, unable to travel freely because it was constantly scattered by charged particles. Then, a critical event that scientists call recombination occurred. As the universe's temperature fell to around 3,000 Kelvin, electrons were captured by protons, forming neutral hydrogen atoms. This act made space transparent, finally allowing photons to travel unimpeded. This initial burst of light, the most ancient we can possibly detect, is what we now call the cosmic microwave background, or CMB. Today, this relic radiation bathes us from every direction in the sky as a faint microwave signal, with a temperature of just 2.7 Kelvin, a mere fraction above absolute zero. At a glance, the CMB appears perfectly uniform across the sky, but incredibly precise instruments like the COBE, WMAP, and Planck space telescopes have detected minuscule temperature variations, fluctuations of only a few thousandths of a degree. These tiny inconsistencies were the primordial seeds from which all future stars and galaxies would grow. Analyzing the cosmic microwave background is like deciphering an ancient text that details the universe's infancy. Its patterns have allowed scientists to pin down the universe's age, its geometric shape, and its composition. 5% ordinary matter, 27% dark matter, and 68% dark energy, all while confirming that the universe began in the hot, dense state we know as the Big Bang. Interestingly, you can even pick up a trace of this ancient light right in your own home with an old analog television. When you tune to an empty channel and see the screen filled with static, about 1% of that visual and audible noise is actually the signal from the cosmic microwave background. It is a faint echo of creation that has been traveling across the cosmos for nearly 14 billion years to reach you. As you drift towards sleep with this idea, you can picture yourself enveloped in an unseen, ancient light, a gentle, nearly ageless glow that silently narrates the origin of everything we comprehend. We typically perceive gravity as the force anchoring us to the Earth or guiding planets in their orbits around stars. However, in Albert Einstein's theory of relativity, gravity is presented not merely as a force, but as the warping of spacetime itself, caused by the presence of mass and energy. When immense objects move or collide, this distortion can propagate across the universe in the form of waves. These are not vibrations in air or water, but rather ripples in the fundamental fabric of reality, known as gravitational waves. Einstein foresaw their existence in 1916, yet he doubted they could ever be detected due to their incredible faintness. To generate a gravitational wave strong enough for us to notice, truly colossal masses must be in motion, such as merging black holes, releasing energy on a scale rivaling the entire light output of the cosmos. For a very long time, the concept of gravitational waves was purely theoretical. The first piece of indirect evidence appeared in 1975, when astrophysicists Russell Hulse and Joseph Taylor observed a binary system of neutron stars whose orbit was steadily decaying. This orbital shrinkage perfectly aligned with Einstein's predictions, indicating that the system was radiating energy away as gravitational waves. Yet, their direct detection remained elusive until 2015, nearly a century after Einstein first proposed them. That year, the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured a subtle chirp with its laser instruments, a signal originating from the merger of two black holes 1.3 billion light-years from Earth. For a brief moment, the fabric of space-time here was stretched and squeezed by a distance smaller than a proton's diameter, and yet the equipment was sensitive enough to register it. Today, gravitational waves have opened up an entirely new field of astronomy. Where we once explored the universe exclusively through light, from radio waves to gamma rays, we can now effectively listen to it, capturing the tremors of space produced by its most violent events. Dozens of mergers involving black holes and neutron stars have already been recorded. These observations are also deepening our understanding of how heavy elements are forged, as the collision of neutron stars seeds the cosmos with gold, platinum, and other precious metals. As the sensitivity of our detectors continues to improve, it's possible we might one day capture gravitational waves from the Big Bang itself. This would be akin to hearing the very first moments of the universe's birth, providing an auditory counterpart to the visual information we have from the cosmic microwave background. Contemplating this as you fall asleep, you can imagine that the space around you isn't still, but is constantly vibrating with the echoes of distant cosmic dramas, a celestial music we are only now learning to hear. Among the most mystifying and captivating phenomena in the universe are black holes. They emit no light of their own and permit nothing, not even photons, to cross their boundary and escape. This threshold is called the event horizon, a definitive point of no return. Anything that passes this line disappears forever into the black hole's depths. The notion of such objects was first considered in the 18th century, when Jean Michel and Pierre-Simon Laplace theorized that stars could exist with gravity so intense that light itself could not break free. A genuine understanding, however, had to wait for Einstein's general theory of relativity in 1915. Shortly thereafter, Karl Schwarzschild derived a precise mathematical solution that described a spherical object with this kind of extreme gravity. Black holes exist in various sizes, from stellar mass black holes formed from the collapse of massive stars and weighing several times as much as our Sun, to the supermassive variety at the centers of galaxies, which can be millions or even billions of times more massive. The origin of these giants remains a profound puzzle in astrophysics, with theories ranging from their birth from the first massive stars to their rapid growth through consuming matter and merging with each other. Despite their name, black holes can be surrounded by some of the most luminous phenomena in the cosmos: accretion disks. These are brilliant, swirling vortexes of superheated gas and dust, orbiting the event horizon at temperatures of millions of degrees and blasting out intense radiation, especially in the X-ray part of the spectrum. In 2019, using the Event Horizon Telescope, humanity captured the first-ever image of a black hole's shadow, located at the heart of the galaxy M87. This landmark achievement served as a powerful confirmation of Einstein's predictions. Even more speculative hypotheses exist, suggesting that a black hole might conceal a tunnel through spacetime, what we call a wormhole. In this view, falling into one might not be an act of total destruction, but a passage to another state of being we cannot yet fathom. While often portrayed as cosmic predators devouring everything around them, they are not nearly so indiscriminate. Lying in the dark and picturing these silent cosmic sentinels, you can feel that they aren't just emblems of an end, but possibly portals to something entirely new that we have not even begun to imagine. Consider the possibility that entering a black hole is not an act of total destruction, but a transformation into a form that currently eludes our comprehension. While black holes are commonly portrayed as cosmic devourers, indiscriminately consuming everything around them, their nature is not quite so voracious. Should a star or planet avoid venturing too close, it will simply continue on its path, completely unaffected. As you lie in the dark and contemplate these silent guardians of the cosmos, you might feel that they represent not just an ending, but perhaps a doorway to something new, something we have not yet even started to conceive. If you can picture a black hole as a celestial trap from which nothing escapes, then its perfect counterpart is a white hole. This theoretical object is something that nothing can enter, but from which everything is violently expelled. Imagine a cosmic spring gushing forth from the very fabric of space-time, a fountain that spews out matter and energy while never taking anything in. The concept of white holes arose from the mathematics of Einstein's equations, revealing a symmetrical solution where time seemed to run in reverse. While in a black hole everything is drawn relentlessly toward the center, in a white hole, everything is instead propelled outward. To date, there has never been a direct observation of a white hole, and some scientists argue that such phenomena might be impossible, requiring conditions that no longer prevail in our universe. Others, however, speculate that white holes could indeed exist, though they would be exceedingly rare and fleeting. An even more audacious hypothesis proposes that a white hole might serve as the exit point from a black hole, forming the opposite end of what is known as a wormhole. In such a case, anything that falls into a black hole in one corner of the universe could re-emerge from a white hole in a distant region of space, or perhaps even in another dimension entirely. Some theorists have even posited that our own Big Bang could have been the result of a stupendous white hole coming into existence. According to this idea, our entire universe is the consequence of matter and energy being ejected from some other realm. Another captivating notion suggests that microscopic white holes could manifest as the final stage of black hole evaporation, a process described by Stephen Hawking's mechanism. At the conclusion of its existence, a black hole might burst in a final flash, casting its remaining matter out into the cosmos. While all these ideas are purely theoretical for now, exploring them helps us to better grasp the fundamental laws of the universe and push the boundaries of what is possible. As you drift toward sleep with this thought, you can envision a point somewhere in the deep expanse of the universe, from which light and matter perpetually erupt. It's like a cosmic exhalation that we can never breathe in, yet one that continues to forge the destiny of entire worlds. Neutron stars rank among the densest objects in the cosmos, surpassed in density only by black holes themselves. They are the remnants of massive stars that conclude their lives in a supernova, a cataclysmic explosion that blows away the star's outer layers while its core collapses under its own immense gravity. The resulting pressure is so extreme that it forces electrons to merge with protons, creating a sea of neutrons. What remains is a colossal sphere made almost entirely of neutrons, so dense that a single teaspoon of its substance would have a mass of billions of tons. These stellar objects are remarkably small by cosmic measures, usually only about 20 kilometers across, yet they contain a mass similar to that of our own Sun. This incredible compactness endows neutron stars with gravitational fields of unimaginable strength. Some of them spin at breathtaking velocities, rotating hundreds of times every second. These rapidly rotating objects are known as pulsars, so named because they emit focused beams of radio waves or light that sweep across space like a lighthouse, creating a regular pulsing effect when observed from Earth. Pulsars have proven to be an indispensable instrument for cosmic exploration, enabling us to measure universal time with a precision greater than atomic clocks, and even to hunt for gravitational waves. Within this category, a special class of neutron stars called magnetars exists. Their magnetic fields are trillions of times more powerful than Earth's, capable of warping the very structure of atoms. A single flare, erupting from a magnetar's surface, can unleash more energy in 1/10 of a second than our Sun produces in 100,000 years. The internal composition of neutron stars remains a profound mystery, with some hypotheses suggesting that their cores may harbor a state known as quark-gluon plasma, a form of matter that existed in the first moments after the Big Bang. Neutron stars are frequently found in binary systems, orbiting a companion. When two such objects spiral into each other and eventually merge, they unleash powerful gravitational waves and scatter heavy elements like gold, platinum, and uranium across space. This means that the precious jewelry on our planet may very well have been forged in the crucible of these cosmic collisions. As you drift off with these ideas, you can imagine a tiny, unbelievably dense star spinning in the distant cosmos, its rhythmic light a signal sent across the void. It's almost as if the universe is knocking on the door of our awareness, reminding you that even the smallest things can hold a power that is truly without limits. Quasars stand as some of the most luminous and powerful phenomena in the entire universe, with a brilliance so intense it can eclipse that of whole galaxies. Their name is short for quasi-stellar objects, because they initially appeared to be simple stars. The reality, however, is that quasars are the hyperactive centers of very distant galaxies, fueled by the supermassive black holes that reside within them. As immense quantities of gas, dust, and even entire stars are pulled toward the galactic center, they form a swirling accretion disk around the black hole. Within this disk, the material is heated to billions of degrees, causing it to radiate a staggering amount of energy across the entire electromagnetic spectrum, from radio waves to X-rays. Because quasars are situated billions of light years from us, we are observing them as they existed in the remote past, when the universe was in its infancy. Some of these cosmic powerhouses release energy equivalent to the light of trillions of suns, and their powerful jets can penetrate the vast stretches of intergalactic gas, shining like cosmic searchlights. It is for this reason that astronomers refer to quasars as the beacons of the distant universe, illuminating the very dawn of cosmic time for us to see. Remarkably, quasars provide us with a tool to investigate not just the objects themselves, but also the vast expanses of space that lie between them and our vantage point. As light from a quasar travels across the cosmos, it passes through clouds of gas and dust, allowing scientists to analyze this light and understand the composition and structure of the intergalactic medium throughout billions of years of cosmic evolution. There is a compelling hypothesis suggesting that quasars were far more prevalent in the universe's distant past. It's plausible that in their early stages, every massive galaxy experienced an active phase where its core blazed as a quasar, only to dim as its central black hole consumed all the nearby fuel. Some researchers propose that quasars could even be tied to phenomena that took place shortly after the Big Bang, meaning that by studying them, you and I might get closer to unraveling the mysteries of dark energy and dark matter. Contemplating this before you drift off to sleep, you can picture an unimaginably bright fire burning somewhere in the silent depths of the cosmos, billions of light years from here, fed by matter spiraling into an abyss. This ancient light has journeyed toward us since the dawn of time, and as it gently reaches our eyes, it serves as a reminder that we are witnessing the faint echoes of a cosmic drama that is still unfolding. Nebulae are immense clouds of gas and dust scattered throughout space, often spanning tens or even hundreds of light years across. They manifest in various forms. Some radiate with brilliant colors, while others appear as dark silhouettes, obscuring the stars behind a thick veil of cosmic dust. More significantly, nebulae are not merely stunning celestial vistas. They are crucial actors in the life of the universe, serving as the very places where stars are born and later die. Among them are emission nebulae, which glow because their gas has been ionized by intense radiation, typically from young hot stars, whose ultraviolet light causes the surrounding material to shine. A prime example is the Orion Nebula, a stellar nursery located just 1,300 light-years away, where new stars are actively forming as we speak. In contrast, reflection nebulae do not produce their own light, but simply scatter the light from adjacent stars, often taking on a bluish hue, like the nebula surrounding the Pleiades star cluster. Dark nebulae operate differently by absorbing light, which results in mysterious black shapes set against the brilliant backdrop of the star-filled sky. A distinct classification is reserved for planetary nebulae, which, despite their name, are not sites of stellar birth, but rather the remnants of stellar death. When a star similar to our Sun runs out of fuel, it expels its outer layers, creating an expanding cloud of gas that is illuminated by the hot, dense core left behind, a white dwarf. Even more spectacular are the remnants left by supernova explosions, which occur when massive stars meet their end. The Crab Nebula, for instance, consists of filamentous structures that are the glowing debris of a star that detonated in the year 1054, an event that was recorded by astronomers of that era. Nebulae are not just passive cosmic decorations. They are dynamic participants in a grand cosmic cycle, as the gas and dust from dying stars provide the raw materials for subsequent generations of stars and planets. This means the very atoms of carbon, oxygen, and iron that constitute our bodies were forged inside stars and once drifted within these magnificent clouds. As you fall asleep with these ideas, you can imagine a massive cloud slowly churning in the depths of space, a place where future stars, planets, and perhaps even new forms of life are beginning to coalesce. Life that might one day gaze upon its night sky and recognize the nebula from which it emerged. Only a few decades ago, the existence of planetary systems around other stars was a matter of speculation for astronomers. Today, we have confirmed the existence of thousands of exoplanets, worlds orbiting stars outside our solar system, with new discoveries happening nearly every week. This progress was made possible by revolutionary advances in telescope technology and the development of methods sensitive enough to detect the subtle changes a planet causes in its star's light or motion. The most successful detection techniques include the transit method, which observes the slight dimming of a star's light as a planet crosses in front of it, and the radial velocity method, which measures the gentle wobble of a star caused by a planet's gravitational pull. It was primarily through the transit method that the Kepler Space Telescope unveiled thousands of new worlds, demonstrating that planets are the norm in the galaxy, not the exception. Exoplanets astonish us with their incredible variety. We have found hot Jupiters, which are enormous gas giants orbiting so close to their stars that their temperatures can climb above 1,000 degrees Celsius. There are also super-Earths, rocky planets larger than our own, which could possess oceans hundreds of kilometers deep. And then there are truly alien worlds, where it might rain molten metal or glass, and the skies are painted in colors you can hardly imagine. Scientists are especially focused on identifying planets within the habitable zone, the orbital region around a star where conditions could permit liquid water to exist on the surface, a vital component for life as we understand it. Some of these potentially habitable worlds are just a few dozen light-years away, which is practically our cosmic neighborhood. With every new discovery, the probability that life exists on other worlds continues to grow, suggesting that somewhere, another civilization might be looking at its own star and pondering the same questions we do. As you fall asleep with this knowledge, you can envision the night sky of a distant planet, a sky with 2 or 3 suns, or with luminous rings reflecting starlight, or with giant moons drifting silently overhead. Although we cannot yet travel to these places, the sheer thought of their existence makes our universe feel infinitely more alive and mysterious. When you think of planets and moons, you likely conjure images of warm worlds with atmospheres and perhaps liquid water. However, both within our solar system and beyond, there exists a whole category of icy worlds, celestial bodies that are cold, yet far from inert, and in some cases might even be habitable. This group includes the massive moons of the outer planets, like Europa orbiting Jupiter and Enceladus orbiting Saturn, as well as Ganymede, Callisto, and even dwarf planets such as Pluto and Eris. These worlds are typically encased in thick crusts of ice, but beneath these frozen surfaces may lie vast, dark oceans of liquid water. This water is kept from freezing by internal heat generated within the moon's core, or by the immense tidal forces exerted by the giant planets they orbit. For astronomers, Jupiter's moon Europa is particularly captivating, as it stands out as one of the most promising locations to search for life beyond Earth. Concealed beneath a crust of ice, several kilometers deep, Europa probably holds a liquid ocean containing double the volume of all the water on Earth. On Saturn's moon Enceladus, the Cassini mission identified geysers that erupt with organic molecules, the very raw materials from which life could emerge. In this way, these worlds act as pristine time capsules, preserving the conditions of the early solar system. The thick ice on their surfaces provides a shield against cosmic rays, resulting in a protected environment that has remained stable for billions of years. This suggests that any life that might have sparked there could have developed in relative security, thriving in total blackness and fueled by chemical reactions instead of light from a star. The allure of these icy worlds extends beyond the quest for life, as they offer scientists deep insights into planetary formation and the distribution of water in the nascent solar system. Just try to picture yourself on Europa's surface. A vast, dark sky is above you, with the immense disk of Jupiter gliding across it, while kilometers of ice are beneath your feet, concealing a vast, churning ocean we cannot see. As I drift to sleep considering this, it becomes clear that these are not just frozen wastelands. They are portals to undiscovered forms of life, and to entirely new chapters in the cosmic story we have only just begun to read. Back in 1916, Albert Einstein proposed that space and time are not a fixed backdrop for events, but a dynamic fabric that can be warped, stretched, and compressed by mass and energy. He theorized that monumental cosmic events, like the merging of black holes, would create minuscule ripples that spread outward. For decades, these so-called gravitational waves were little more than an elegant mathematical concept, a prediction confined to the pages of theory. The predicted ripples were so incredibly faint that their detection was thought to be an impossible task. Then, in 2015, a breakthrough changed astronomy forever. For the very first time, the LIGO observatory captured the signal of gravitational waves from two black holes colliding, a billion light-years from Earth. This finally validated one of the last major unproven tenets of relativity. These waves are fundamentally different from anything else we can detect. They are not light or particles, but are instead disturbances in the geometry of the universe itself, which travel unobstructed through all matter. As a wave passes through our planet, it infinitesimally squeezes and stretches space by a distance smaller than the width of a single proton. To perceive such a microscopic effect, scientists engineered massive detectors that use lasers to monitor distances with astonishing accuracy. Now, gravitational waves serve as an entirely new sense for exploring the cosmos, enabling us to listen to cosmic events that are invisible to traditional telescopes. This new astronomy allows us to detect the mergers of unseen black holes and even witness the creation of heavy elements when neutron stars collide. Future plans include launching space-based observatories like LISA, which will offer even higher sensitivity, potentially opening a window into the universe's first moments. As I consider all this before sleeping, I can picture those silent waves from faraway cosmic disasters passing through us at this very moment, carrying with them the history of billions of years. A quiet whisper from the universe, imperceptible to us but audible to our most advanced instruments. When you gaze up at the night sky, it feels like you're seeing the entirety of existence laid out before you in stars, planets, and galaxies. The truth, however, is that all this visible material makes up just a small fraction of the cosmos. The vast majority is concealed in a form we've named dark matter, an enigmatic substance that is completely invisible, but whose presence we can infer from its powerful gravitational pull. The story of how we discovered dark matter starts with studying the motion of galaxies. During the 1930s, an astronomer named Fritz Zwicky observed that galaxies within clusters were moving with such high velocity that the gravity from their visible stars shouldn't have been enough to hold them together. Decades later, Vera Rubin's work provided further proof, showing that stars on the outer edges of spiral galaxies orbit just as fast as those near the center, a feat that defies the laws of physics if you only account for the matter you can see. The sole conclusion that fits these observations is the existence of a huge amount of unseen mass that generates the extra gravitational force. This substance neither emits nor reflects light, and is completely indifferent to electromagnetic radiation. yet its gravitational influence is what keeps galaxies from flying apart and sculpts the grand-scale structure of the cosmos. Scientists theorize that dark matter is composed of elementary particles we have yet to discover, which interact only feebly with the matter you and I know. Prime candidates include WIMPs, an acronym for weakly interacting massive particles, axions, and even theoretical dark counterparts to protons and neutrons, though decades of searching have yielded no direct evidence of their existence. Despite its elusive nature, dark matter is fundamental to the story of cosmic evolution, as without its presence, galaxies and stars might never have come into being. Computer simulations reveal that its unseen filaments formed the foundational scaffold upon which the entire visible universe was built. There are even more speculative ideas, such as the hypothesis that dark matter is made of miniature black holes that originated in the moments immediately following the Big Bang. If this is true, then you are quite literally surrounded by the most ancient objects in creation, older than any star or galaxy. Contemplating this as you drift off to sleep, you can picture everything we perceive as mere islands of light suspended within an unseen ocean. It's a reminder that perhaps one day, we will finally understand what lies concealed in the darkness that invisibly holds our entire universe together. While dark matter works to attract and bind galaxies, dark energy accomplishes the exact opposite. It forces space to expand, pushing everything apart at an ever-increasing speed. This discovery stands as one of the most profound and baffling revelations in modern cosmology, completely reshaping our view of the universe. Until the close of the 20th century, the scientific consensus was that gravity would gradually slow the universe's expansion after the Big Bang. However, in 1998, two separate teams of astronomers observing distant supernovae found something startling. The expansion wasn't slowing down at all, but accelerating. To account for this, the concept of dark energy had to be introduced. Today, our measurements indicate that dark energy constitutes approximately 70% of all mass and energy in the universe, but its fundamental nature remains a complete mystery. One theory posits that dark energy is an intrinsic property of space itself, a concept known as the cosmological constant, which Einstein once added to his equations only to later dismiss it as his greatest mistake. An alternative explanation suggests dark energy is a dynamic field, a kind of quantum ether that fluctuates over time. You can think of its effect as an invisible anti-gravity force that stretches the fabric of space-time, and as space expands, more dark energy is created, feeding a cycle of runaway acceleration. In the far distant future, this process could lead to some truly dramatic outcomes. If dark energy's dominance persists, galaxies will eventually recede from one another until they vanish from our sight. An even more extreme possibility is the Big Rip, a moment when the expansion becomes so violent it shreds galaxies, stars, planets, and even the atoms themselves, though such an event would not occur for many billions of years. For now, dark energy stands as one of science's greatest puzzles, and as you fall asleep with this idea, you can envision the universe as a silent ocean, its shores relentlessly stretching and carrying all things, galaxies, worlds, and even our own dreams, farther and farther apart. Our entire cosmos began in an unimaginably hot and dense state. Roughly 380,000 years after the Big Bang, it had cooled sufficiently for atoms to coalesce, which finally allowed light to travel freely. This primordial light, is what we now call the cosmic microwave background, or CMB, the most ancient electromagnetic radiation detectable. It permeates all of space, arriving from every direction as a faint echo of the universe's birth, and was first found by accident in 1965 by Arno Penzias and Robert Wilson, who detected a persistent, strange hiss on their radio receiver no matter where they aimed it. We now understand that the CMB is our most valuable source of information about the nascent universe. When observed with highly sensitive instruments, it reveals minuscule temperature fluctuations, or anisotropies, which correspond to the distribution of matter in the moments after creation. These tiny variations were the seeds from which all galaxies, stars, and planets would eventually grow. By studying the cosmic microwave background, scientists have pinpointed the age of the universe at about 13.8 billion years and determined its composition. Around 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB is more than just a scientific instrument. It's a poetic testament to the fact that you can literally see our world's past. Every photon from this radiation has journeyed for nearly 14 billion years, traversing the vastness of space and bearing witness to cosmic history. Falling asleep with this realization, you can imagine yourself enveloped in this invisible, ancient light. A soft, almost infinitely old glow that quietly narrates the story of how everything you know began. When you contemplate the cosmos, your thoughts often turn to the past, to the Big Bang, the birth of stars, and the assembly of galaxies. But it's only natural to wonder how this story concludes, and what fate awaits the universe in the remote future. Scientists have put forward several scenarios, each as fascinating as it is unsettling. Among the most probable is the heat death of the universe, a theory suggesting that the expansion fueled by dark energy will persist without end, leading to a cold and empty final state. Over trillions of years, stars will inevitably exhaust their fuel and die out, leaving galaxies desolate and barren, aside from the cold, dense remnants of white dwarfs, neutron stars, and black holes. In this distant future, all energy and matter will have spread out evenly, bringing the universe to a state of maximum entropy, a final, silent equilibrium, devoid of all heat and movement. A far more violent, though less probable outcome is a scenario known as the Big Rip. Should the mysterious force of dark energy prove to be unstable and grow stronger over time, the expansion of space could accelerate to cataclysmic speeds. This process would methodically dismantle all cosmic structures, first tearing apart galaxies, then obliterating star systems and planets, and ultimately disintegrating the very atoms that constitute reality. Yet another possibility for the universe's end is the Big Crunch, which would occur if the relentless pull of gravity were to eventually overpower the expansion driven by dark energy. In this model, the cosmic expansion would halt and then reverse, causing everything to collapse inward. Galaxies and stars would rush toward one another, temperatures would skyrocket, and the entire universe would finally converge into a singular, intensely hot point, perhaps setting the stage for a new Big Bang and the birth of a new cosmos. Beyond these theories lie even more speculative ideas, such as the Big Bounce, which posits that the universe is locked in an eternal cycle of expansion and contraction. There is also the multiverse hypothesis, suggesting our entire cosmos is merely one among countless others, rendering its ultimate conclusion a minor event within an infinite tapestry of different worlds. No matter what the ultimate destiny of the cosmos may be, one truth remains certain. We have this present moment. This is our time to look up at the heavens, to investigate the stars, to pose profound questions, and to pursue the answers. Contemplating the universe's final chapter might just be the key to helping us grasp the profound value of every instant we are alive. As I consider this while falling asleep, I imagine some future being, a distant human descendant or an entirely new form of intelligent life, looking out into their night sky billions of years from now. I picture them attempting to comprehend what our era was like, a time when the universe was still in its youth, teeming with an abundance of brilliant light.